Hey, everybody. So welcome. I'm just going to say a few words while people are still popping in. I'm Robert McDougal, and I'm joined today for this tutorial by Bill Lytton, Adam Newton, and Salvador Dura. And we're going to be talking about Neuron and NetPyNE. You've probably already seen this, but this is linked off of the CNS website. This is a brief overview of the schedule. Bill's going to start us off. I'm going to talk about Neuron, Adam's going to talk about reaction diffusion, and Salvador is going to talk about graphical and then programmatic uses of NetPyNE. All of these times are in US Eastern Time. For doing this, while we're doing all of this, we have CNS, as you probably figured out, is using Discord, which I may or may not be sharing right now. It was certainly my intention to share Discord. I think I'm sharing it. In any case, CNS is using Discord channels to organize all of the communication. So please feel free to, during these tutorials, ask questions on the Discord channel T1. This is tutorial number 1. Yeah, we'll get to them. We'll have somebody monitoring during the talks, and anything that's needs to be addressed, we'll bring it up to the speaker to make sure it gets addressed to a group as well. And by using Discord instead of Zoom chat, we'll have a permanent record. We can always go back and check this out. So should be great. Again, very excited that you all could join us. Does anybody have any sort of procedural questions before we begin? All right, and everything, I should also mention that everything that we're doing today is going to be based on the cloud, so you don't need to install anything, although we're certainly happy to talk about how to, how to run Neuron locally, how to run NetPyNE locally as well. So
if they're recording all this, Robert?
Yes, all of this is being recorded. You should have gotten a notification when you joined. If not, all this is being recorded. So with that, if there's no procedural questions, I will turn it over to Bill Lytton to talk about implementing the conceptual model.
The talk now should be.
I think you're sharing what you want to share.
That's wonderful. Okay, so title overview of modeling, really, implementing the conceptual model. And the reason for making that the title, which I actually changed from last year, is that I realized that many people don't appreciate what we're trying to get at, and not just Neuron and NetPyNE, but many modelers, in terms of broadening the scope of what is computational neuroscience, which has traditionally been pure electrophysiology in the tradition of Hodgkin-Huxley, as well as, of course, all the offshoots for artificial neural networks in the tradition of Hopfield and backpropagation and now deep learning. So there's a focus in our thinking as a broader group, and the group has really been led for decades by Michael Hines at Yale, of putting the electrophysiology into context, so that the electrophysiology is just one piece, and it's a piece that takes place at a certain scale of the cell. And that scale is the size of a cell, which is maybe 30 microns across for a soma, and maybe as large as a whole millimeter for an apical dendrite, as well as a couple meters for your giraffe neuron that's projecting down to its toes, to the extent that it has any toes. And this has a spatial scale here, logarithmic on the y-axis, and it has a temporal scale, logarithmic on the x-axis, and the scale of an action potential, which was the original study by Hodgkin and Huxley, would be order 1 to, in the squid, several milliseconds. But again, this is just for us, the center, because sorry, it changed, because that's where we have studied most. It's the kind of thing like in the story of the blind man and the keys. The blind man loses his keys. He's looking around at night under the lamp, and somebody says, "Oh, can I help you? What happened? I lost my keys." And I say, "Oh, you lost them under the lamp? And he said, no, I lost them way over there, but this is where the light is. So you look where the light is. You look where you can do the experiments, basically, and where you can find things out, and you don't look at other places where we still are in mystery. One other key point here is that the cell, although it is, of course, biologically a unit, metabolically a unit, can be thought of in many ways as having a distinct.
Yeah, might just be.
Probably somebody needs to be muted. I'm hearing somebody in the background. Having a distinct identity. That was the argument between Golgi and Cajal, that Cajal won. It does have a distinct identity. It informationally may very well not be the proper unit because it's so embedded. Let's speak of neocortex. Everyone studies neocortex more than other areas, but this is true in other areas as well. It's embedded in a network of layers where most famously the layer 5 cortical cell is reaching up to layer 1, and there's stuff going on up there and we don't understand what it is. And the tufts, there's other inputs coming into layers 2, layer 3, other inputs coming in via layer 4, which are direct inputs in sensory areas from thalamus. And so there's this interaction, this overlap of layers, which you don't necessarily see in many other systems, that makes us further, as is further complexity. I also want to emphasize that we need to get, for the purposes of using any of this for therapies, for using it medically, for using it for neurological and psychiatric disease, we need to get down to the molecular scale because that's where the drugs are. So we need to get down to receptors. We need to get down to second messengers. We need to get down to things that are going on really down low. And we also want to get up to high things. Of course, if we're interested in cognition and consciousness and all the cool stuff, that's all very high up. And we need to think about that in terms of Shannon information theory. But also just for again, clinical usage, you'd want to get up to EEG and fMRI and BOLD. So many temporal scales, many spatial scales. Even more classic than Hodgkin-Huxley, back to Ramon y Cajal, back a century and a quarter now, I guess. The neuron doctrine, the dynamic polarization of the neuron says inputs come into the dendrites, go to the soma, go out the axon. Well, that's useful as far as it goes and is probably true in many cases, but there's many aspects of that that are oversimplified, as with any dogma. Famously, Francis Crick elaborated the central dogma of DNA. DNA makes RNA, makes protein. And then someone, a bunch of guys who, and a gal, I think, who discovered the retroviruses, said, hey, and they wrote to Crick, they said, hey, here we've got an example where RNA makes DNA. And Crick said, no, that's impossible. It's not my dogma. But dogma doesn't take you very far in biology, for better or worse. Better in the sense that there's always something new there, always something different, always a different organism, always a different brain area doing something different. And worse, of course, in that you've just got this endless complexity, which can be discouraging. So what's wrong with the neuron doctrine? Well, one thing is that even in cells of this type, you have some anomalies. You have backpropagating action potentials, pretty clearly shown. And so things are not just moving in one direction. You may have issues in the axon, maybe I'll mention that later. And certainly you have all kinds of issues at the synapse, mention that later. Another thing is, yeah, well, that neuron doctrine might hold pretty well for pyramidal cells here in the upper left, but when you get to the thalamic nucleus and you have thalamocortical cells, and in particular their interaction with thalamic interneurons, you have these complex dendritic triads, which are dendrodendritic synapses, which actually was another thing that went against a dogma. And the people who worked on that originally were Gordon Shepherd at Yale, who's something of Robert's mentor there, Gordon Shepherd Sr., working with Wilfred Rawl, and they tried to publish this stuff, and a lot of people would not accept it at the time. Purkinje cell, I'd say maybe one of the cells that's more of a classical Cajalian neuron doctrine cell, but a little peculiar because even though it's a principal cell, it's an inhibitory cell. And so not really the way you think about, in the way Cajal and Laurent Deno thought about cells activating other cells. Well, this is a cell that's inactivating other cells, even though it's a principal cell and not an interneuron in its system in the cerebellum. So complexity, variation, variability, endlessly. So how do we form a concept of our neuron? Well, this is the classic concept from Rawl, which builds on the classic concept from Hodgkin and Huxley. The parallel circuit, the parallel conductance model, it would be one of these little blobs here, and these parallel conductance models are now connected by resistors to form compartment models. And so you might, here very schematically shown, you might have a neurolucida of a cell, and then you turn it into these, what in neuron are called sections. I'm going to change how I use this pointer. And then you change it into this electrical equivalent. So this is the classical concept. This is the concept. And then immediately you have to ask, as with any concept, what's missing? What are you going to include? What are you going to leave out? Well, one of the things you're going to leave out is the ions. So you've taken the ions, which are sodium ions, potassium ions, and their associated channels, the ion channels, the classical sodium, fast sodium channel, the classical delayed rectifier, KDR channel, and you've reified them. That's one of those cool words. You've implemented them as rheostats attached to batteries. The battery coming from the membrane dissociation across the membrane of sodium and potassium. And so you've lost everything about the ions themselves. Well, we put back the ions, and this is a figure from Adam Newton who will be speaking. And now you suddenly have this great aura around the neuron, in this case, an aura of potassium. And you can see that things are changing around the neuron and spreading out from here the soma and proximal apical dendrite and affecting other parts of the neuron quite possibly, and certainly in the case of what we call spreading depression or spreading depolarization, getting a change in membrane potential in other parts of the cell as well as in other cells. So you put back one of your initial concepts and you get a very different model than you had with the conceptualization as an electrical circuit purely. Again, you can go endlessly with this. Here's further complexity. But much of what we're trying to attack, we're not at all trying to attack most organelles, except for endoplasmic reticulum, which we're very interested in, and many groups are very interested in, because calcium, in the words of Rama Blackwell, is the answer to everything. We don't know what it's the answer to, but it's surely the answer to some things, because it's everywhere and it's always communicating with other between channels, between metabotropic synapses and channels, involved with cyclic AMP, involved with IP3, involved with G proteins. It's very important. It's stored in the endoplasmic reticulum, which is everywhere inside the neuron, which has these foliations that fill areas, and it looks really cool in EM. As neurons themselves do. So it's something we're very interested in. Many groups are very interested in. Other second measures also very interested. And the synapse, famously shown by Eccles to be many synapses, most synapses to be chemical synapses. Here again, we have this transmission, and there's such complexity. And of course, we do have to simplify. We're never going to get the full synapse, probably, but we have to decide how much complexity we want to keep, how much complexity we want to leave out, what our concept is, what our idea is for that cell. So Hodgkin-Huxley equations, you're all familiar with. At rest, we have a large potassium flux because of the N infinity curve. We have this in volts. That's odd. Okay. Usually we speak in millivolts, so this is negative 50 millivolts. At rest, we're down here, maybe negative 70, negative 80, so we have substantial amount of the N. Where's the N? That's the blue. And we have de-inactivation of the sodium channel, which is why you have a relatively high level of the H particle, so-called H particle. However, you don't have much flux through sodium because here you do not have any activation, here the M particle of the sodium channel. So as you push the voltage up with an EPSP over here, you now will start to get activation. So you'll be moving to the right on this curve, activation of the M particles, there are 3 of them in this case, as well as inactivation of the KDR. So that will start to come down, the H particle, 4 H particles as it happens. And because the sodium channel gives you a positive feedback system, this activation, the M going up, leads to voltage going up. And voltage going up, here moving along the x-axis from left to right, leads to more of the M opening, M particles, the 3 M particles. And so that's the positive feedback. This goes up, forces this to go up. This goes up, the M goes up, forces V to go up, and so on and so forth until you reach this peak where you have a balance between the forces of pushing you up, the positive feedback, and now the negative feedback kicking in. There's a balance here between the sodium and potassium currents, because as you've gone up, you've gradually gotten more de-inactivation of the potassium. Where's that? Here, sorry, potassium. And so the N has gone up as well, more slowly because its tau N, is much longer. So its kinetics much slower than the kinetics of the sodium activation. And so that's what gives you the delay. And now you get the negative feedback part, where as it comes down, you, well, actually, sorry, this is not really negative feedback. It is negative feedback overall, but here as you come down, you get more de-inactivation of the potassium channel. There, I think I got that all right. So that's the classical model. Now, another way of looking at this, actually the same model, is to put it into the context of a Markov model. And so you then have this kinetic gating scheme for just the sodium channel, only the sodium channel, for that, for the Markov. And here, what you're talking about now is really at a different scale. So in the Hodgkin-Huxley model, whoops, we were talking about a population. It doesn't follow very fast. A population of ion channels that together function in this concept of positive feedback and negative feedback. And here you're really conceptualizing a single channel that works in a Markovian historyless manner to turn on a channel. And these are all states where one of these M particles changes, or going down, one of the single H particle changes, and you can go between any of these states with certain kinetics. Those kinetics are all very closely related because this is a very simple, it looks complicated, but it's a very simple Markov model in terms of the kinetic values and in terms of what states are available. The only state that is conducting is this state where you have all 3 M's set to 1. So all of the 3 M's are on. These are, you can think of as little gates. That's how they are really. In this model, again, conceptualization, the little gate opens for M, opens for another M, opens for a third M, and then also has to be open. And in the case of Hodgkin-Huxley, we speak of that opening as the de-inactivation. Has to be open, four gates open, and you have now the state down here in the lower right, which is the state of a open condition. So with that model, you get very different results. And here is what I think is really one of the neatest little easy simulations in Neuron, which I want to show now. And that is that as you add channels of the Markovian type, you gradually get closer and closer to a action potential that you would see using the full Hodgkin-Huxley model. So here with just 10 channels in blue, you have quite a lot of variability. In particular, sometimes you have something that is not a action potential at all, and you wouldn't identify that as an action potential. You wouldn't even know what it is if you saw that curve. We have time on the x-axis, only 5 milliseconds. We have voltage on the y-axis between positive 40 and negative 80 millivolts. And we have this response from 10 channels opening up randomly, pseudo-randomly, because of course it's a simulation, at the times indicated here. You can see there was an opening here pretty much at what you'd think of as the right time, but then there wasn't another opening for a while, and then not another opening for a while. And so you got something, that was not an action potential. However, randomly, when doing 10 channels again, randomly, I got something that was quite a bit more like an action potential. And then I increased from 10 to 100 channels. And now you're doing a lot better. I think that would be this green one. This green one is starting to look a lot more like some kind of action potential. It does not match the conductance of the full Hodgkin-Huxley model. Okay, so then we can go to 1,000 or 10,000. And as we get to 10,000, I think I couldn't make these two different colors because they were too close together. 10,000, you're doing really well. And I just wanted to show this because it's fun to play with. And this is actually the old Neuron Demo, and it uses the old GUI, which was the interviews GUI. And this is something we have to update. And if anyone in the audience wants to learn some very basic plotting routines and basic routines in Neuron, this would be a great task for somebody to do. But here we bring it up, and already we can see that it offers us a variety of different cells. So we can bring up a stylized cell, which, let me see if I can bring it up here, is just like this ball and a couple sticks, or we can bring up a full pyramidal cell. So that would be now another concept, a far more detailed concept, a morphologically detailed concept of the neuron. And we can bring up we have artificial cells here. So a network of artificial cells. And we have one that's labeled no model. And this one is some kind of a synaptic release model. I guess there's no picture associated with that. Okay, so the one I want to show is stochastic single changes Hodgkin-Huxley. So here we have that model. And let me go to line type so we can keep lines, and we'll go, this is again something I don't want people to really learn because we really have to get this into Python graphics. And we want to get a thicker brush because otherwise it can be hard to see. And might as well make it red. And if we now start by running with 10 channels, we should get, so hit init and run, and that's not very thick. I guess I have to click on it to make it thick and red. There it is. Not a very attractive action potential. And you'll see that this is random, pseudo-random, because every time you do it, it'll look different, but it looks bad. Whereas when you go to 100 channels, and I don't know if I can change the color. I'll try. Let me see. Init and run. And then I change the color to blue, and I find the one that we just did. I'm not sure which one we just did. Init and run. That one is this one. It's looking somewhat better. Init and run. Init and run. Some of these are pretty darn good, but they have a lot of problems right at the threshold. Right at the threshold, just a couple guys go off, and those couple guys give you a big boost, and now you are generating up from there. Go to 1,000 channels, better yet, and go to 10,000 channels, and you'll see that it's going to look really like an action potential. And in fact, we can then switch to the continuous, which is the full regular Hodgkin-Huxley solution, and it'll just lay on top of the ones we just did, so you don't see anything. So that's a thing that's just fun to play with. Again, it needs to be translated into Python, but it's there already. And if anyone didn't notice how I brought it up, it's from a command line. If you have Neuron installed, Neuron Demo. And assuming that Neuron IV is in your path, Neuron Demo will be in your path, and it will bring this up with all its mod files compiled, and we'll run these different simulations. So just to kind of summarize, electrophysiology is what we know most about, and we're now moving into chemophysiology. We want to deal with intracellular and extracellular reaction diffusion. We want to see how the brain works at that level. We want to understand spines, which really are a mystery. Are they chemical reactors or electrical reactors? We want to understand more the details of synapses. We have the cleft where we have diffusion, but it's really very close. So it's a different kind of diffusion, and it's in a very detailed matrix, probably somewhat different kind of diffusion than out in the regular space. Even the regular space is really a jello and not water. Future directions might include more medical aspects. Since stroke is the major neurological disease, we would want to consider the vasculature someday in the future. Just to say that in thinking about modeling, we always want to think about being back and forth with biology. So we want to predict, we want to get data from biology, we want to make predictions for biology, we want to have somebody test them, ideally in vivo, but maybe at least in vitro or in a cell culture. And you know, everybody always complains, hey, your models are not detailed enough, they don't include enough, they're leaving all this stuff out. Well, when you do a slice, it's also leaving out a lot of stuff. When you do a neural culture, it's leaving out way more stuff. So everyone leaves out stuff. And of course, again, the idea of you're just looking where you can shine the light, so you're not really seeing everything. Today, we're going to talk about neuron, we're going to talk about reaction diffusion, and we're going to talk about NetPyNE. And there are several resources, of course, the main pages for each of these, Neuron and NetPyNE, as well as misspelled ModelDB, where it has an enormous number of models. So thank you. Any questions? Let's see, where did the meeting go? Here's the Discord. Okay. The specific implementation, because I just looked at it yesterday, I was curious, has to do with the HH-Chan mechanism in Neuron, which I've never used, and it allows you to set up specific kinetics that run relatively fast for that set of individual cells. Okay. Other questions, or I guess you can speak also if you want. We are adding rule-based chemical reactions. Robert, how far did we, or Adam, how far did we get with adding rule-based? We had at one point Boolean chemical reaction concept. Anybody want to address that?
I would say right now we're really sort of on the world of kinetic schemes, kind of a basis wherein we know the kinetics, we keep track of every state explicitly. The internals, so we had a version that would translate, you know, and instantiate every specific possible state permutation. But one of the things that you can do very efficiently with rule-based is, say I have a protein that has 1,000 phosphorylation sites or something like that. You definitely don't want to keep track of every possible state, because there's way more of them than you actually have molecules. And so we don't have any explicit infrastructure, but somewhere when that's not the case, we do have some ability to actually explicitly instantiate everything. It's a work in progress.
Yeah, and it's worth mentioning that Neuron is now opened up entirely as an open source project with contributors like you, just like they say at the NPR stations. that, you know, anybody who wants to get involved, and this is be a great project, somewhat difficult, I think, to put something new together. We can orient you to the Neuron Dev GitHub, and the it has its own Slack channel, etc. We generally want people who are pretty darn sophisticated with Python and with Neuron to be working on that, but there are many of you either like that already or will be like that. And similarly with NetPyNE. NetPyNE also has its whole development project. I see that Robert is typing. You can talk, Robert. Oh, no, here, something.
No, I mostly just said what I already said.
Okay, very good. All right, I will now pass it on to Robert, I think.
Yep.
And now I have to stop sharing screen, which means I have to find the screen where I'm sharing from. Oh, there's something. Stop share.
Wait, hold on. No, I lost him. Sorry, so I'm going to be, while I'm doing this, I'm going to not be monitoring Discord. So I'm hoping Bill, Adam, Salvador, really anybody who knows the answer to a question can address any questions that come up. And if anything is urgent, go ahead and give me a shout out. All right, so so basically, so first of all, thank you, Bill, for that introduction. So I'm going to start with a brief overview of Neuron itself. I'm going to talk a little bit about some concepts and some basic scripting, focusing on electrophysiology. So this is going to be done with sort of a mix of slides and exercises. In the interest of time, I invite you to do these exercises along with me. But we're going to kind of just keep going through, and we're not going to have a long amount of dead time where people are struggling with things. So after all of that, I'll hand it over to Adam Newton, who is going to talk about reaction diffusion kinetics. I'm very excited that people have already started to think about that on the Discord. Such a sort of chemical phenomenon that happen inside and outside of cells. So if you want to track potassium as it spreads across, you know, as potassium concentrations across the extracellular space, Neuron's happy to do that for you. Yeah, so again, please use the Discord, and everybody's going to try and monitor that and get going. So with that, does anybody have any questions before we begin? All right, so. All right, so Neuron, as you guys know, is a general tool for simulating neurons and networks of neurons, including the extracellular space. It's especially focused on models involving biophysically detailed cells with morphologies and ion channels. And that's what we're going to talk about today. But there are more abstract models. So you can do Zakevich and things like that. That also runs really well. And Neuron has some specialized infrastructure for doing integrate and fire very efficiently. We're not going to get into that today. You can find examples of this on ModelDB. We're not going to talk about this now either, but since Bill brought it up, I'll mention that Neuron provides a graphical interface that allows point and click modeling and analysis. We've also got a newer work in progress tool that allows you to build graphical interfaces without having to learn any sort of Neuron specific techniques. So this is all sort of HTML based. But if you know fancy GUI libraries like WX or Qt, you can incorporate Neuron visualizations into your interface via Plotly or Matplotlib. Neuron plays well with sort of all of your generic Python graphics libraries. Also, since Bill mentioned Neuron development, if you're interested in getting involved, we'd love to have you. Our meetings are every third Friday of the month, 10 a.m. US Eastern, 4 p.m. Central European. When these disagree, it's mildly problematic, but But most of the time, these are the same things because the daylight saving time switches differently. So yeah, so we have monthly developer meetings. The agenda is posted on GitHub. Meetings are mostly public on Zoom. We're welcome to have you, but we do keep the Zoom link private to avoid Zoom bombers. Just send me or anybody that's talking here today an email for the Zoom info. All right. So for this session, we'll focus on using neuron via programming, which is the most powerful way of running and analyzing simulations. So we don't need to know a lot of Python syntax or write a lot of code to do something useful. I am going to, my apologies if you don't know any Python, I am going to have to assume this. I can point you to resources that will allow you to make some sense of this, but I will try and describe everything at least as to what it's doing. So here, for example, this is the complete code that we need to make this interactive graphic that we see here in the top left. So first we begin by loading neuron. So from neuron import H, that's how we connect to neuron. H is kind of the main neuron component. We're going to do most of our interactions through H. So for example, when you see h.load file, this is how you tell neuron to load a specific neuron library or some other saved data. And then from an import or sort of Python's way of loading Python libraries. So I can load age, I can load some unit specifications, millivolts and milliseconds in neuron's default unit, so it doesn't really affect us here, but it is nice to document everything and have units nice clearly. So we load a bunch of libraries, we can load a morphology file, so this is C91662, we'll see later we can get a vast array. I think there's over 150,000 now of neuron morphologies from neuromorpho.org. You can load all of these into Neuron. So here I've loaded Neuron, I've loaded a morphology. I got this file. This is available. This file specifically, you can search ModelDB and find it. If you don't know ModelDB, it's a resource for sharing models and discovering models for computational neuroscience specifically. Has some nice visualization and analysis tools that you might not find, for example, if you're using GitHub. I'm gonna check. Nope, I'm not gonna check Discord. Just to see if there's anything on there because I keep hearing beeps. All right. So anyway, so actually what I'm gonna do, I lied. I'm gonna quit Discord so I don't hear beeps. Okay, so anyway, so ModelDB is a great way to get example morphologies. We can get these from neuromorpho.org. So anyway, so here's what we've done. We've loaded Neuron, we've loaded a library, we've loaded a morphology. H.HH refers to that Hodgkin-Huxley channel. It's HH, right? So we can take that, we can insert it into all sections. So H.allsec is all sections. We're going to add a current clamp. We're going to put the current clamp in a specific location, and I'll talk more about this later. I just want to give you a sense of what's happening. And so what this is saying is the current clamp is going to start at a time of 1 millisecond. It's going to stay on for a certain period of time, and it's going to have a certain amplitude in nanoamps. So I have, in the left column, I've constructed I've loaded some libraries, I've loaded my cell morphology. In the middle current column, that top line says, hey, I got Hodgkin-Huxley channels everywhere. And then the next batch is sort of the stimulus that I want to give, right? There's going to be a current clamp. Once we've got that, I can say that I want to initialize my simulation, and you can set all kinds of initialization rules. But the simplest thing that you can say is that you want to initialize it to a certain membrane potential everywhere. And then the way the Hodgkin-Huxley channels are implemented, when you do that, it will initialize the gating variables to the corresponding steady state values as well. And then I can say that I want to run this for 2 milliseconds. Once I've done this, I can construct what's known as a plot shape, which is a graph that plots the shape of the cell. So I can construct a plot shape. I can say I want to plot a certain variable, namely voltage here. And then, so this is just a syntax. I'm going to plot that variable using Plotly. It's my graphics library of choice these days, that and ggplot. But you can use matplotlib as well. It's custom color map just because, and then we show it. And so then we get this interactive figure here. You can mouse over it, see what voltages are where. That's sort of the deal. So we've done, and I don't know how many lines this is, but something on the order of, I don't know, 18 lines, less than 20 lines, I'm sure, of code. We have done everything that we need to set up a cell, give it some kinetics, give it a stimulus using a current clamp, run the simulation, and sort of plot the steady state, plot the temporary instantaneous membrane potentials. We could also record time series. We could visualize 3D things. All of this stuff is pretty easy to do in a relatively small amount of code. It's kind of formulaic to a certain extent. It's using Python. If you know Python, you can do lots of fun things like bring in databases when you're doing parameter sweeps and all kinds of for loops. But really, the basics are, I think, fairly straightforward, and we'll get to them in more detail. When we talk about networks today, we're going to use NetPyNE's graphical model specification tool, but that's just a layer that's sitting on top of Neuron for simplifying network specification, parallel simulation, but you can do all of this directly. One of the nice things about NetPyNE is that we can always go back and refine anything that's specified using lower level Neuron functions. So to give a sense of the scale that's possible, I'm just showing a 2014 simulation from Michele-Maiori that used Neuron directly to simulate about 40,000 cells. And they ran this across a little over 2,000 processors on a Blue Gene computer. So Neuron is perfectly happy scaling to these larger models. Now your desktop doesn't have 2,000 processors, but if you're interested in really large simulations like this, your institution probably has at least one high performance computer that you can get access to. And if not, there's the Neuroscience Gateway, nsgportal.org, which provides free access to HPCs for neuroscience simulation. And they officially support everything that we'll talk about today: Neuron, NetPyNE, and lots more. So today we only have time for a relatively quick introduction of Neuron, focusing on concepts and using it through the cloud. But I hope this will give you enough information to start doing something and to put the tutorials. So they're sort of in two places right now, which is a little unfortunate, but some of them are under the documentation link on the homepage. And there's also a function by function and class by class level breakdown of programmer's reference. So this is shown here for the graph class, for example. So hopefully this gives you enough information to put all of these things that you read in context and to make sense of them and to do many, many more things. So there's also tutorials links. So this is hosted by Read the Docs. You can get there directly, nrn.readthedocs.io. And so in this, there's additional tutorials, and these are a bit of a work in progress as we're moving things from Neuron website to Read the Docs. As we do so, we're updating them. We're trying to make everything directly runnable in the cloud so you can experiment with stuff without having to install Neuron directly. You know, you can literally run some of these things from using Google Colab on your phone, which is very exciting for me the first time I did that. So we wanted to make this as accessible as possible, but that transfer is taking a little bit of time. So if you'd like to keep learning, so if you're excited about what you've learned here today, so we do have an official YouTube channel, which you can get to by tinyurl.com/neuronvideos. So we'll put this recording up, of course, as soon as it finishes processing. But in particular, I also want to highlight that within the on the Neuron YouTube channel, we have the 2021 Neuron online course playlist, which is an online webinar series that we've been doing. We're about a month in, and it's continuing for another month or so. So unfortunately, enrollment in the interactive portion is closed, but all of the videos are recorded. They're publicly accessible. So right now there's about 16 hours worth of material from that Neuron course posted. on the website. We're adding new videos twice a week. And it's going to end up being something around 30 to 40 hours of instruction on Neuron. So I encourage you to check that out if you'd like to learn more than we were able to get to today. So today we're going to run everything in the cloud using Google Colab. So strictly speaking, you don't need to install anything for today. But if you did, this is how you do it. You'd use pip, the current version of Neuron. So Neuron's currently 8.0. Unfortunately, pip only supports Mac or Linux. However, if you go to the Neuron website, you can get a binary installer if you're using Windows. So just go to neuron.yale.edu, and then down at the bottom there'll be a download link, and it'll say download 8.0, and you'll have the Windows installer. If you're doing this, you're going to want to install on your local machine. You're going to want to make sure that you have Python available. Again, Mac or Linux, that you probably already do. Personally, I use Anaconda. And there's some other things that you can install. So like MPI is necessary if you're going to do parallel simulations, but really installation should just work, and this will give you the basic setup. So before we get into this, does anybody, since I don't have the Discord channel open, is there anything that anybody wants to talk about, or sort of background before we actually go and try and do something? Okay. So if not, so we can actually, to actually get to using Google Colab, we can go, this is colab.research.google.com. It's going to pop this up. I can go to File, New Notebook, and I can just create a new Jupyter notebook. I said, there we go. And once I've done this, let me actually make this a little, yikes. Sorry. Stop. Stop. Sorry. Where is my notebook? Okay, so when I'm doing this, I can, for example, so if I'm using Google Colab or any cloud provider, they don't have Neuron installed, but it's pretty easy because I can just do !pip install Neuron. And this works even if you're on Windows because this is running in the cloud, right? So if I do !pip install Neuron, oh, I said I was going to make this bigger. Come on. Why are we not making this bigger? There we go. So cool, I can do !pip install Neuron. I have Neuron available now. And then if I want to connect to Neuron, I'm going to start out with from Neuron import H. And then there we go. So right now, that's it. I have a working install of Neuron. I'm able to do whatever I want. And I invite you to play along with me here. So this I got here from colab.research.google.com. All right, so let's say, so this is how we connect to Neuron. This is a way of connecting to Neuron in the cloud. You can use any other cloud provider. All of this is going to work basically the same. You can run this locally. If you run it locally, obviously you only need to install Neuron once, and then your Python scripting would start out the same. So does this make sense? Is there any questions on any of this before I move on? All right, cool. So here we are.
Adesso c'è uno, perché
I'm sorry?
eh, 15 minuti, lui fa una pausa, poi forse smetto anche.
I'm sorry, could you try one more time? I couldn't quite understand. Oh, now I can't hear anything.
I think that was just a background person. I was trying to mute all, but I didn't know if I got them.
Oh, okay. All right, well, if there was a question, please post it on Discord, and we'll get to it there. All right, so let's suppose, okay, so before So anyway, so that's basic. That's the basics of how we connect to neuron. We can load from neuron input H, we can do from neuron.units, and we can load, say, whatever units we want, millivolts, milliseconds. There's other libraries. But yeah, so this is sort of this is my recommended way to, at least maybe a Jupyter notebook, not necessarily Colab, is my recommended way of interacting with Neuron. And it's going to play nice with all of your Python graphics and all that. So how do we actually do something with Neuron? So let's talk a little bit about background. So if you think about what's actually needed to do a simulation experiment, you've got your conceptual neuron, and this is going to have some morphology, some ion channels. You're going to do some experimental perturbation, right? So maybe you're going to add a current clamp to prompt the neuron to fire. It's going to have some data of interest that you want to monitor. And then you're going to want to make a pretty picture and see what you've done. So we'll look at each of these in turn. So in Neuron, the basic building block of a neuronal morphology is the section. A section is going to be defined as an unbranched piece of cell. So if you look at, so this is your cell, and there's a soma, and it's got a long stretch coming off, and then there's a branch, and then there's a branch, and then there's a branch, and then there's a branch. Well, each one of these straight pieces, where they're not broken up, could be thought of as a section. All right, it's just a section of the cell that's relatively straight. So the soma is a section. The apical trunk might be a section. All of the branches coming off of the apical are sections. Their branches are sections, and so forth and so on. All right. So in Neuron, you create a section using h.section. Remember, we're going to access everything through the h submodule. So if I want to create a section called soma, I'll say h.section, I'll give it a name. So name equals soma, and then I will assign that to a variable. And if this seems redundant for you, the reason that we do this is because we can certainly have multiple variables that are referring to the same object, right? So you could imagine I've got my soma, but when I'm looping over sections, if I'm looping over all the sections within my cell, I'm going to have a variable that's going to be referring to this, and my for loop variable is going to be referring to the soma sometimes and to other things other times. So we need to sort of separate the concept of the name and the variable. And you can always ask Neuron to tell you what the section's name is, what cells are associated. And in fact, if you know programming, I'd encourage you to use what's known as object-oriented approach and create, instead of building everything at the top level, to create everything inside of a cell class. And the advantage of that is that you can then sort of define, this is what pyramidal cells look like for my model. Test one pyramidal cell, and then when you're happy with that one pyramidal cell, you can just ask Neuron to say, okay, now give me 1,000 of these, and then I'll connect them in a network, and then I'll do whatever. And I think fundamentally NetPyNE will do some of this logic for you. And so that's part of another reason that we might want to use NetPyNE on top of that. All right, so neurons are composed of individual pieces that are sort of stuck together. Well, how do we stick them together? Each section has what's known as a connect method. So I could say that one section is connected to another, and I'll show you exactly how to do that in just a second. And sections have certain properties, and this includes things like the length, the diameter, and a numerical discretization in a 1D spatial compartments known as segments. So InSeg is this discretization. So what we're going to do is if I have a long path, I don't want to calculate 1 voltage for maybe an apical trunk, right? Maybe that apical trunk, if I go to, I can't calculate a continuous variation because computers don't work with continuous things, but I can say at a certain location, the membrane potential is whatever, and then at a different location, the membrane potential is something else, a different location. And so what I'll do is I'll chop that section up into multiple pieces. And so maybe InSeg is 3, and I'll chop a section into 3 components, and I'll calculate 3 membrane potentials. I'll calculate 3 sodium concentrations. I'll calculate 3 Hodgkin-Huxley state variables at the very, one for each of the locations. And then so you could imagine that if I wanted to test, make mathematical statements about convergence, I'm going to want to be able to refine my spatial discretization. I'll increase it by an odd factor, just because if I do that, then all of my nodes continue to exist when I refine it, right? So I can say, well, okay, I've gone from 1 to 3. Well, my old node is now my center node. And then I can just keep track of the membrane potentials and all the state variables that I'm interested in. And am I getting the same thing as I've refined all of that? So that's sort of an empirical approach to assessing convergence. There's some theoretically principled ways of getting at least a appropriate starting point. There's something known as the d lambda rule that Neuron supports. And I'm happy to chat about that in Discord later if anybody has any questions on that. Yeah, so the other fundamental thing that I wanted to point out about a section, well, sections have a beginning and an end, right? And so the way that Neuron represents things, position along a section, we don't talk about the third segment because that's a property of, how we chopped it up mathematically. We want to think about a certain fraction of the way down a section. And so the way that we do this is we say, here's the beginning, that's the 0 position of the section. Here's the end, it's the 1 position of the section. And so we're always going to refer it to normalized distance along a section. Although if you want, there are ways to convert between normalized distance and physical distance. Well, actually, it's pretty obvious, right? You just use a scale factor of the length of the section. One other detail that I want to point out, just because this is a confusing point for some people, so here you could imagine, I'm showing section as having 1 diameter. In fact, every segment could have its own diameter, and more so than that, we're not actually limited to assuming that cells are not made of cylinders, right? Cells, you don't have an abrupt transition of diameters. And so the way that this is done with Neuron, we can have arbitrarily varying diameters, arbitrarily varying paths. And so Neuron's perfectly happy with that. It'll do this automatically for you if you load a morphology from like Neuromorpho. And otherwise we can chat about this later if you have a question. So, all right, sections. Cells are made of sections. And sections have normalized position. So let's see if we can do something. So we pulled up a Google Colab. So let's go back to, nope, that's not going back to. Let's try this again. Let's go back to our Google Colab from earlier. All I did was pip install Neuron from Neuron import H. Again, I encourage you, if you've got another screen or you want to make this smaller, to go ahead and do this along with me, just to make sure that everything works for you. So we start out loading Neuron. So then let's say, so from Neuron import H, that's a main thing, but I like to talk about units. I like to document my units. So even though I might not have to, strictly speaking, because I'm going to start out using Neuron's default units, it's good to be able to write all of these things down. So from Neuron.units, import millivolts and milliseconds. I'm putting this all, just for the record, I'm putting this all in Jupyter Notebook. You can certainly run exactly the same code in a Python script if you're familiar with that way of using code. So from Neuron.units, import millivolts and milliseconds. And then if I wanted some graphics, I could say import Plotly. And I use Plotly mostly just because it plays really nicely with Google Colab and gives us some interactive stuff. All right, so let's say that I want to start out with something very simple. All right, I want to have 3 sections that are connected to each other. And I'll have it so that I have a main thing and it's got 2 branches coming off of that. All right, so how would I do that? Well, I do it by creating some sections, first of all, right? So let's say that I'm going to say that I'm going to create a main section. Main is h dot section. Name is main. You'll notice that as I type here, and I'll have a branch that's coming off of this. As I type, it is suggesting things. So if I can't remember what something's called, I can always just start typing it, or how something's spelled. I can always start typing it, and it's going to be kind enough to Google's going to be kind, well, Python really is going to be kind enough to auto suggest these are all of the things that you could extend this with. So it's giving me a little bit of information. This is a thing that returns a new section. That's really cool. I mean, mostly personally, I just ignore those things, but it is very convenient to have. If you don't like it, you can always hit escape and then they go away. So here we go. So I've created a section, and I've created 3 sections, one called name, one called branch 1, one called branch 2. One other gotcha if you're not used to Python. Fundamentally, things only exist if you have a way to access them, right? So if for some reason I were to overwrite the variable main, or if I defined all of this inside of a function, and then I didn't return whatever I defined, then there'd be no way to get back to those objects, right? Like if I were to say main is none here, which I won't actually run, but if I were to say that, then main doesn't exist anymore. Well, then I have no way of getting to main anymore. And so Python's rule is if you have no way to access an object, then the object doesn't exist. And so any effects that you'd have, any simulation details would just disappear. This is actually a strength that makes it really easy to modify your models. You just overwrite them, you just change them, and everything just works. But it may be a gotcha if you're not used to it. So that's why I mentioned this. So anyways, I've created 3 sections. And so how do I actually see them? So I can see them by creating what's known as a plot shape. It's the thing that's going to plot the shape. We already saw this earlier when we had the full cell. I'm going to pass in the variable of false. What that is, I actually don't even think I have to do that here, but if you're running locally, it'll stop it from popping up an interview style window, the graphs that Bill showed earlier. And I'm going to say I want to use plotly to plot it, and then show me the picture. Show me the pretty picture. And if I do this, I see a graph which has 3 lines. One of them is called main, one of them is called branch 1, one of them is called branch 2. And by default here, it's plotting the membrane potential. So the membrane potential is -65 because I haven't done anything. That's fine. We'll ignore that. So I've defined 3 sections, but I haven't actually connected them in any way. So you'll remember, and I can zoom, I can rotate, I can do all of the things that you think you can do because it's 3D graphics on the web, right? So now, how do I actually connect them together? So, you know, it's nice that my cell has 3 parts, but cells are usually connected together. In fact, the cell's not in one piece, that's a problem. So in order to do this, I'm going to say branch 1, I'm going to connect it to my main section. You know what? Branch 2, I'm going to connect to my main section. And that's it. So I now have 2 sections that are connected to my main section. And if I want to see if I did this right, I'm just going to rerun that plot command. I'm going to plot it on Plotly and show it. And now, what did I do wrong? How did I do this wrong? What? Oh, I know why it's upset at me. Sorry, I'm just going to go ahead. And so what happened was when I made that first plot, it decided which way the shapes were, and they were all laid out horizontally. So when I connected them together, since they were already positioned in space, it just attached one to the end of the other. And so it kept the orientation, which is actually a really nice feature because then you can sort of detach bits of dendritic tree and move it around. But it did sort of come back to bite us just now. So here, what I've done is I've gone back up, I've reran this. By the way, if you don't know, I should have said Shift Enter or hitting the play button will run it. So I've rerun it. And now if I just skip the initial plot and I connect them, and now I plot everything. The old one is still there, but the new guys are up here. I do apologize for sort of getting that presentation messed up, but does that make sense? So there were in fact in the original version there were still 3 sections in a line. It's just that 2 of them were coincident because they originally had the same orientation. All right. So now let's say, for example, you'll notice though that there's only ever 1 point in each of these sections. Well, there's everything shows main as 0.5. Why? Because there's only 1 numerical compartment that's associated with this. So no matter where I am on this branch, it's going to tell me that I'm at the middle position. So the notation here is the section, parentheses, the normalized position. So if I wanted, however, to do something at a higher resolution, because like I said, probably it's not all that useful to have everything be just 1 compartment. Let's go back and say main is going to have a different number of segments. That's the number of places that I compute. Maybe main has 11 segments. And now if I pull up that plot shape, and if you're doing this for real, you just make a function for this and you don't keep typing it every time. But now if I pull up, it obviously looks the same, but as I move over main, I see a whole bunch of different locations. All right, there's a section at a variety of points. Okay, well, what does that mean for us? So that means that at each one of these locations, I can assign a different value, right? I can have a different voltage. I can have a, so let's say, for example, that, how do I want to do this? So let's say, for example, so main is composed of is a section. It has a number of segments. Each segment has a normalized position. So what we can do, for example, one of the things that's super great about Neuron, we can loop over those segments. So if I have for seg in main, so remember main is a section. It has many segments. So this is looping over every single section, every single segment within that section. And then I can print out, let's actually just print out the segments. Let's just look at what main is made of. So if I were to print out the segments, I have main at, what is this? Well, main at 0.045, main at 0.136, and main blah, blah, blah at 11 total different locations, evenly spaced down the section. And I can also, everything has a location, right? So I could grab that normalized position if I want with seg.x. I could grab its real position by taking seg.x and multiplying it by the length of the main. If I wanted to see which section it was, I could ask for seg.sec. and it's going to tell me that every single one of these is in my main section. And why do I do this? Well, let's suppose that what I'll do instead, so I can loop over these things and get a lot of information out of them. Let's suppose that what I really want, because this is neuroscience, I'm really interested in potentials. So let's say that every segment is going to have a certain membrane potential, that's seg.v. And let's just say for simplicity, let's suppose that its membrane potential is just its position along the section. So seg.v, I'm going to just assign to increase linearly with position. So sure enough, so now I've set membrane potential along my main section. Obviously, we're going to have Hodgkin-Huxley or whatever kinetics that we actually want do this for us, but just to get something to look at. So let's go ahead and pop up a plot shape now. So now if I make this, I can say, by the way, I want to plot a certain variable. I want to plot voltage. I could just as easily say that I want to plot sodium, or I want to plot, you know, whatever, but I want to, or a gating variable. I'll plot the voltage, and then I'll go ahead and plot this using Plotly, and I'll show it. Oh, and I'll do this too. I'll set the scale. Well, let's just run it as is and see what happens. So you'll notice as I mouse over this, it does change color a little bit here, right? So here I've got main is at position 0.45 is at 4.5. As it goes up, it gets bigger and bigger and bigger as I move towards the one end of main. The color scale is not very convenient because I've got -65 is my low end. So what I can do is I can specify and go back up here and say, you know what, I actually want, set the scale, set the color bar to be between 0 and 100. And then that's easy enough. And so now 0, anything lower is blue, and it goes up to purple. We've already seen in the example earlier, and I don't want to belabor this point because I think I've spent more on this than I intended, but we can specify color maps. We can do all kinds of things like that. Does anybody have, so this is, so we've defined our topology, basically, is what we have here. And there are ways of specifying the curve through 3D space if we actually care about that. And there are reasons when we might. But this at least gives us sort of the basic topology. Everything here, by the way, you may have noticed that everything here has a certain length. So let's see what the defaults are. The defaults, so here's the length. I didn't specify it, so it's defaulting to 100. I didn't specify the diameter, so it's defaulting to, thank you, by the way, for posting the plot code. The default diameter is 500, and this is in microns. And I mention this for a couple of reasons. Mammals don't really have 500 diameter anything. But you know who does? Squid. Squid giant axon. That's a reasonable diameter for squid giant axon. You know what else? Let's look at so temperature, right? One of the things that we're very concerned about, well, might be concerned about, is temperature. And certainly as temperature increases, we expect sort of more molecular activity. And this has implications for a lot of ion channel models. You have to explicitly encode this in your ion channel models. But the Hodgkin-Huxley implementation that we have certainly does. So the default temperature, H.Celsius, is 6.3 degrees. Perfectly fine for a squid, not fine for a mammal. So I mentioned that just as a way of, by way of warning. Make sure, punchline is, make sure you don't assume defaults without checking, right? Just, you're better off specifying parameters, but be aware that there are things going on behind the scenes. Oh, here's another one for you. The axial resistivity. of a squid is something like 35.4 ohm centimeters. For a mammal, if I want to do a mammal, I'd probably want something more like 100 ohm centimeters. So any of these values that I can read, I can also set using the equal statement, which is fairly common for programming languages. Anybody have any questions on any of this? All right, so just to get back to the slides then. So when I'm doing this, so I showed you that I could plot the variable voltage. I could just as easily plot any other state that neuron cares about. So here's concentration, so I could plot the sodium concentration, sodium current, sodium reversal potential. Heck, I could even plot the relationship between current and membrane potential. Why not? I could plot gating variables, and not showing you this here, but basically, so and you can just sort of swap out. This is the sodium concentration because it's NaI. If it was the calcium concentration, it would be CaI. We'll see later on that we need things known as pointers. It means exactly what you think it means if you're a programmer. But we can get the pointers, which basically lets us talk about not the current voltage, but the voltage at a location as it varies over time. And so there's a formulaic method where you can take the names that you pass as a string, the plot shape, to get the pointers for a given segment, and so forth. And I think this is easiest when we actually have examples. I'm not sure if there's a question or if all right, so I'm going to mute somebody because I don't hear a question, but if there was a question, just go ahead and unmute yourself. All right. Sorry. So we've defined our morphology. Ion channels are going to be, of course, our next part of our conceptual model specification. These ion channels are going to be inserted into sections using either the sections insert method or the mechanisms insert method. And we saw this earlier in my initial example that we can use the Hodgkin-Huxley mechanism. So H.HH is the Hodgkin-Huxley mechanism. I can insert it into a single section, or if I have a list of sections, like, my entire cell, or maybe all the axons, I can do that in one line, H.HH.insert, and then wherever it goes. You'll remember in the previous slides, there was a H.allsec, which is the list of all sections. If you have a given section like a soma, you can say soma.wholetree, and that'll give you all of the sections that are attached to the soma. There's all kinds of stuff you can do, but all of this kinetics is collapsed down inside neuron into the concept of H.HH. But we don't have an overwhelmingly large number of ion channel kinetics that come with neuron. We prefer to let you make sure that things work the way you think they should. But fortunately, neuron's been under development for over 40 years now. And so there's a rather large number of these of ion channel kinetics that you can pick from. Hundreds of them are available on ModelDB. So modeldb.yale.edu. And that's got mod file mechanisms. Yeah, and you can always, and so once you find one of these, you can compile them using NRNIV modal or !NRNIV modal when you're on Google Colab. All right, so here what we've got, so all of the sodium potassium channels, the gating variables, that's all encapsulated in H.HH. We can insert that into the axon as shown here with H.HH.insert. And H.HH is the abstract mechanism that doesn't exist anywhere. But if I want to refer to the HH mechanism within a part of the axon, I access that part. So it'll be like if I have axon of 0.5, that's the middle of the axon. And then I can do .HH. and then that's referring to the Hodgkin-Huxley dynamics within that location. And then I can do a Dura to see what parameters, et cetera, are there. All right. So all of these things are specified using mod files. This is, you can actually go tinyurl.com/hh mod file to see what the mod files are for representation is for the Hodgkin-Huxley dynamics. How exactly they work is beyond the scope of today's tutorial, but like I said, there's hundreds of examples available on ModelDB. You can check them out there. There's also, I also want to point you to this preprint that's available. So if you go to tinyurl.com/inmodal preprint, there's about 60 pages of examples and discussion about how all of this works. It's a little old, it's from 2000, but it, and there are some things that you can do now that you couldn't do then, but generally speaking, everything that's there is still the right way to do things. I will point out that there's a suffix HH, and this is what makes it h.hh inside Python. If it was suffix cow, it would be h.cow inside Python. So you could imagine you have an H channel mechanism, or you have a NAV 3.1 if that was a thing you cared about, or what have you. That's all available there. There's ontological identifiers with the represents keyword. And so this is sort of saying that this, you know, this mechanism represents the sodium channel. The letters Na represents the sodium ion. You can omit this and Neuron will be perfectly happy, but it does help for analysis. One other mechanism, so besides reading the 60 pages of the preprint, one other method that I'll recommend is a lot of people make their models. They find something that's very similar, you know, maybe it has the right number of state variables, but the time constants are wrong or something like that. They find something that's very similar and they modify their ion channel to represent to a different ion channel. That's a perfectly good way of doing this. I do want to point out though, when you're doing that, make sure that you know, either fix the represents to refer to the right ontology identifier or just leave this off entirely. And that's fine. That said, you don't have to write them. Like I said, you can go on ModelDB, such modeldb.yale.edu. You'll find hundreds or maybe thousands of them at this point that are all associated with published models that you can reuse and modify. This is part of the SenseLab project. So if you follow at SenseLab project on Twitter, you'll see announcements of new models. And then, like I said, once you have your mod files, compile them on Colab with !NIV model, NIV model, before allowing Neuron to use them. All right, so we have our cell. It has a general topology. It's got ion channels in there. Okay, now in order to make it go, in order to respond, it needs something to respond to, right? There has to be some sort of stimulus. And there are many ways that we can do this. But one simple means that's built into Neuron is to use the current clamp. So this is specified in Neuron using an I clamp, H.I clamp. And so like synapses, but unlike Hodgkin-Huxley kinetics that we saw earlier, an H.I clamp is an example of what's known in Neuron as a point process. That is kinetics that take place at a point, as opposed to spread out along the section. So all point processes are constructed similarly. As shown here, they take the name of the point process, so H.I clamp, and a segment location. So maybe it's H.I clamp of axon of 0.5. That's a current clamp that's going to go at the middle of the axon. It's got various properties that are associated with it, but most importantly, these are the delay. When does it start? This is measured in milliseconds. The amplitude measured in nanoamps, indicating the strength of the current, and duration, or dur, measured in milliseconds, again, indicating how long the current stays active. All of these may be set using the dot notation. So this will give you a current clamp that stays on as a fixed amount. There are means, and we can talk about them via Discord, if anybody's interested, of having a current clamp that uses a variable stimulus So if you wanted to feed in a sine wave or a ramp or whatever, Neuron's perfectly happy to let you do this. A current clamp is, of course, only one way to cause a cell to fire. You could also do this by directly setting a voltage, using a voltage clamp, triggering synaptic input either from another cell or via an external stimulus. So not shown on this slide, we can also stimulate extracellularly or with semi-arbitrary electrical circuits. And so Neuron lets you do electrical circuit modeling because it helps you understand that. Remember, the values that you record, if you're doing an actual experiment, are not exactly the values that the cell would have if you hadn't stuck a wire into it, right? Because there's resistance, there's capacitance on your wire, but there's also, how have you changed things by injecting stuff or by modifying it. This is especially relevant if you're doing like calcium indicator dyes, because that's going to function as a buffer. But so in any case, there's a number of ways of stimulating a model. You'll have these slides. We'll post these slides on the course webpage. So you can always go back to this and check this out. All right, so once we've gotten so we've defined our model, we've gotten our cell simulated, so it's going to do something, but we're going to need to actually record it, or we don't really have anything out of it, right? So we can record it, we can then throw everything to pandas and dump it to a CSV or do whatever kind of data analytics that we want. But so for example, if I want to know the instantaneous membrane potential at a certain location, we've already seen that I can take this section, specify the normalized position on the section, and do a .v to get the membrane potential. That was in one of our examples earlier. I can do the same thing to access the gating variables, parameters, all of that. Yeah, if I want to record, so that's the instantaneous. That is what is the membrane potential now. If I want to monitor that over time and build a time series up, I will use an h.vector. And so if you know Python, just think of this as a neuron-aware version of a NumPy array. And it's actually directly convertible to a NumPy array. And so you can pass in a pointer to whatever you want to monitor. So in Neuron, time is h.t. That is the current time. If I want to monitor a time and I need a pointer to it, a pointer to that concept, so the way that we do it, the way that we get a pointer is we put underbar ref underbar right before the last thing after the dot. So if h.t is the current time, h.underbar ref underbar t is the concept of time, and that value that's associated with it is going to change throughout the simulation, right? Because the cell was at time 0, then the cell's at some other time, and then another time, and another time. So I can record time and I can record membrane potential. And the reason that I say to record time is because, well, if I don't record time, I don't know when the values are of the membrane potential that I've recorded. And that's going to be a problem because I can't really interpret it, the results. And if you're using like EFEL, which is Blue Brain Project's Python library for electrophysiological features, and you can use this, by the way, for experimental traces or simulation traces, it doesn't matter. You're going to explicitly need to know the values of time that you've recorded and whatever the time series values are for the variable that you've recorded. But it's a great tool to have access to, so it avoids having to explicitly code how to, how do I calculate the action potential half width? I don't want to write that code. Fortunately, they've already done that for us. And there's examples that you can find on the web. And again, if anybody wants to talk about that on Discord, we can do it there later. And like I said, symmetrically, if you have a specific time course, you can always feed it into any variable using what's known as a vector play. Check the documentation on that for more. So we can also monitor for events like a membrane potential that first exceeds a certain threshold. So this is a reasonable way to define an action potential, right? So you could imagine every time that my cell, maybe I'll define an action potential, how do I pick when the cell spikes? Well, let's say whenever it crosses 0 millivolts from below. Let's say that I pick that as my definition of an action potential happening. So if I wanted to record these spike events, right, whenever these action potentials happen, I use what's known as a netcon. And they get the netcons get their name because these are used to connect a network together. And so when an action potential occurs in one cell, one or more synapses in other cells will receive synaptic input. Obviously, there could be different synaptic weights and different delays before they actually get this. But fundamentally, this is how we construct a netcon. So we're going to say, we're going to create a vector to record things, because anytime that we're recording a neuron, we're going to need a vector, a neuron vector. We're going to create our netcon, so h.netcon. We're going to monitor a certain location, so axon is 0.1, so this is the 0.1 location, 1/10 of the way into the axon. We're going to monitor its membrane potential. Importantly for now, we're not going to do anything with this, so we're going to say none, which means we're not sending this to a synapse. If I want to connect it to a synapse, the synapse object would go here. And mildly inconveniently, but we do need to specify what section is associated with the value that we're recording. So we just say sec equals axon because this came from the axon. We'll set our threshold. We want to record whenever we cross 0 millivolts. And then we'll just throw all of those values into the spike times vector. All right, and all of this, we'll have examples for this in just a little bit, and hopefully it'll make more sense. But finally, before we actually get to the examples, how do we actually run the simulation? My advice to you, Neuron comes with a huge number of libraries. One of them is one of the simple, so they've got libraries for loading morphologies, libraries for simulations. So for example, there's the standard run control library. So h.loadfile std_run.oak is going to give us our high level initialization and simulation control. So what we can do, my advice should always use that. We'll initialize our simulation or certain membrane potential everywhere using h.f_initialize, and then we can run our simulation or a certain time period, h.continue run 10 milliseconds. So run this until time 10 milliseconds. If you're already at 10 milliseconds, this will do nothing. But if you want to run it for an additional 10 milliseconds, just take your current time, which is h.t, and add however much you want to run it for. So that's my overview, and then now I'm going to transition into examples. But again, I've not been able to monitor the Discord chat. Does anybody have any questions? Can you please explain how this evolution of membrane potential over consecutive segments is computed, e.g. along a dendrite section of 3 segments? So fundamentally, this is known as using what's known as the cable equation. There's a second spatial derivative in there, but it's cable theory. Does that answer your question, or do you? Okay. All right. So incidentally, all of this, so as an aside, I will say that fundamentally what this means is that Neuron by default, all membrane potentials and all of that stuff is generally calculated in as cables, as branching cables. What that means is if I have a synapse coming in on one side and a synapse coming in on another, but they're in the same position along the neuron, we're not going to see any differences because we're treating everything electrically as cables, and they're all coming in at exactly one point. However, Adam will show us, I think, that we can do 3-dimensional chemical dynamics, and at which point, well, then we can have differences between synapses at different spatial locations. But most of the time, you don't actually need that. Does anybody have any other questions before I jump back to Colab? All right. If not, again, remember, Is there any difference in how membrane potential is computed along segments versus compartments? So the compartments in neuron are segments, and vice versa. Those are equivalent concepts. It's just our name for chunks of dendrite. I think you mentioned that you prefer using Neuron through Jupyter notebooks. I was wondering why, and assuming you were talking about Windows, whether you also think it's the easiest method on Linux. So incidentally, I'm working on a Mac, but for the most part. Okay. Life is complicated, and I have multiple opinions, and they're not always consistent. One of the reasons that I like Jupyter notebooks. I mean, so first of all, you know, you can use like there are cloud providers like Google Colab that allow you to use notebooks for free, and then you don't have to install anything, and you can bust out your cell phone and whip up an example. I've definitely done this. So I think that's fun, and it's a great feature. And then everything is just immediately portable to different environments. Just send somebody a link to your code, and then they can run it and they can play with it. But if you have a bigger model, obviously that's not going to work because the amount of resources that you get for free is limited, and you're going to want to run it locally or on your own HPC. So then the advantage to me of a Jupyter notebook as opposed to a Python script is that it does still give this is the code that I've run, this is the result that I've gotten, this is the code that I ran, this is the result that I've gotten. So I can mix and match, I can see exactly which figures go along with what code, what analysis. I can go back and add some text to these documents, and I can build a story, right? So if in an ideal world, you end up with this document that you can show to somebody who doesn't need to know anything about programming, doesn't need to know anything about Neuron, really. And you just say, this is what, you know, you describe what you did, here's a little bit of code, here's the output, and it's sort of self-documenting, and it really tells the story in one thing. And if you're using some scripts that you need, go ahead and throw them in a separate script, but bring it in, and then you get a coherent story. And then import them in, you know, go ahead and write the separate scripts, but then import them in, and then have that story, that summary document that you can show to your advisor who's not going to want to maybe run everything separately, but what's the story? And then notebooks make it easy to tell the story. That's, I guess, really that. But Neuron is perfectly happy running in Windows, Linux, Mac. You can use whatever interfaces that you want. You can use Python graphics. You can use the interviews graphics. All of that just works. But I like notebooks because they let you tell a story. That's all. All right. So with that, time is ticking away, but come on. You would think, what has happened? Sorry, 1 second. Trying to find my stop. Okay, so let's go ahead and let's generate a. Oh, you know what? I do want to actually go back. Sorry, I'm going to mess with it one more time. So let's go ahead and let's make a new notebook. And let's say that I want to do sort of the simplest thing that I could imagine. I want to create a simple Hodgkin-Huxley simulation at a single point. So you have all of the material, you have all the background to do this. So feel free to do this ahead of me, but I'm going to just sort of talk through my approach. Joe, did you have a question or? Okay.
No, sorry about that.
Yeah, no worries. So I'm just going to go ahead and talk through my approach, but go ahead and try to do this in another window. So again, I'm using colab.research.google.com. If you've got a local Neuron connection, awesome. Go ahead and feel free to do it that way. So, okay, so we saw that if I'm doing it in, yikes, why is life hard? If I'm doing it in Neuron, I'm going to do pip install Neuron. If I'm doing it in Google Colab, I'm going to have to explicitly start my notebook with this line saying, hey, basically, I'm going to need the Neuron library. Cool, it's easy, it's set up in a few seconds. That's all there is to that. So then every time that I do this, I said that there's going to be some basic boilerplate that I'm going to want. So I'm always going to want from Neuron import H, because H is the main thing that we use in Neuron. I'm always going to think it's a good idea to go ahead and import some units. Again, you don't strictly need these, but it makes your code more readable, in my opinion, if you define things. And I'm always going to want to load my standard run library. So I'll h.load file std_run.hook. And I'm always going to start out doing that. Anytime I'm going to do a neuron simulation, I'm going to start out that. These are things that, you know, gives me some options. Okay, for the sake of today, Neuron's perfectly happy, plays very well with basically all Python graphics. I'm sure somebody can find an exception, but I'm going to use Plotly just because I think it works very nicely inside of a notebook environment. And so the main thing for Plotly is this graph objects submodule, which is traditionally called Go. Okay, so I want to see a membrane. I want to see an action potential, right? If we do nothing else today, we got to get an action potential, right? So how do I go about this? So I'm going to have to create a section. I'm going to have to add my ion channels. Maybe I'm going to want to give it some size. That's probably a good idea. And then I'm going to inject some current, let's say. It's one way of getting an action potential started. I'm going to do some vector recording to plot it, or sorry, to record it. I'm going to initialize my simulation. I'm going to run my simulation, and then I'm going to plot my results. That's the broad plan. All right. So let's just see if we can do this. So I'm going to create a section. I'll call it the soma. Name is soma. And I'm going to say my soma is going to have a certain length and a certain diameter. And that's going to be 10 microns. And I didn't actually import microns as a unit. So there we go. Now I have. So there we go. So I've defined my space. I'm going to need to add some ion channels. So H.HH is the Hodgkin-Huxley channels. I'm going to go ahead and insert that into the soma. Again, if you want more channels, you can get them from ModelDB. And then all you need to do is load them in and compile them with !, NRN, IV, MODL. So I've inserted my channels into place. I'm going to go ahead and give a current clamp. Remember, I is what the electrical engineers like for current, so it's an H.I clamp. I'm going to specify a location. You'll see that it's giving me lots of hints as I type, because Python is amazing like that. So, but I'm going to go ahead and put it in the center of the soma. I'm going to say that it's going to start at time 1 millisecond. It's going to have a duration. Well, usually you want the durations to be pretty small. And then it's going to have an amplitude. And I don't have a great intuition for this. What is the right amplitude to get the cell to fire? 2 observations. We can inject a large current. We're not going to kill the cell, right? That's one of the benefits of virtual in silico experiments. We can, if we go too high, that's fine. If we go too low, again, the cell's going to be just fine, and we can always rerun it by changing a line. So I don't have a whole lot of pressure as to how many nanoamps that I want to inject. But let's just say, and I sincerely do not know what this is going to do, but let's say that I'm going to inject 0.1 nanoamps. All right, so I've defined my cell, I've added the channels, I've stimulated the cell with a current clamp. I'm going to need to record it, because otherwise, you know, it's going to do what it's going to do, and I don't know anything about it. So I construct a vector to store all of my results, and I'm going to record the concept of time. So that's h dot underbar ref underbar t. If I wanted the current time, it'd be h dot t. The current time is 0 because I haven't done anything. And then I'll also construct a vector to record the center of the soma's membrane potential. Again, dot v is the current membrane potential. Dot underbar ref v allows me to record the membrane potential as it changes over time. If you accidentally put in dot v, it'll be like, psst, I think you forgot a dot ref. It's not exactly what the error message is, but it's basically what the error message is. So it's generally helpful. So I've defined some instrumentation. I'm going to record it. Let's run the simulation and plot it, right? So in order to run, we always have to initialize. So I can initialize to some membrane potential. Let's say I generally, you can start with -65 millivolts, but you could use a different one if you wanted. And then I'm going to continue run. And I mean, so here I'm starting from the beginning, but if I was 5 milliseconds in and I continue run until 10 milliseconds, it would run it till 10 milliseconds. So let's just say that I'm going to run this to 10 milliseconds, I guess. So there we go. I've initialized, I've ran it. It finished in a blink of an eye. Well, what did it do? Right? So I could look at all of my voltages. You know, voltages are vectors. So let's just print them out as a list. So I typecast that to a list. -65, -65, -60. Doesn't look like it did anything much, right? Looks like my stimulus wasn't enough. But let's make a picture. This picture's worth 1,000 lists. So we'll make a picture, and let's just say that is going to be go.scatter. And my x values are going to be my times, and my y's are going to be my voltage. And then I'm going to show this guy. And what do we get? And if you like, if you know matplotlib or ggplot or whatever you like to use it. But I'm just using Plotly because it gives these nice interactive graphs. So what did we learn? We learned that 0.1 nanoamps for 0.1 milliseconds wasn't enough to get our cell to fire an action potential, right? There's no regenerative phenomenon. We get this abrupt rise, but only to -62 millivolts. We don't, you know, it wasn't enough. So, okay, well, what do? We can go back and say, well, maybe instead, what if my amplitude was 1 nanoamp? Cool, let's find out. We'll just rerun this. There we go. So 1 nanoamp brought us up here for 0.1 milliseconds. And then it starts to sag a little bit, but the sodium channels switch on and we jump up and we get this action potential and so forth. So are there any questions on that? So, okay, so we've gotten a single action potential, but obviously most of the time we don't have one value that we're interested in. We have many that we're interested in. So let's say maybe instead, well, okay, we know that 0.1 wasn't enough and 1 is enough. So let's just make a parameter sweep. Let's see how sensitive this model is to various inputs. So the way we do a parameter sweep in Neuron is a for loop. Cool. So let's just say that for the current clamp amplitude, so IC.amp is the current clamp's amplitude, and we're just going to try a whole bunch of values. So 0.1, 0.2, 0.3, 0.4, 5. And there are other ways of writing this, and if you know Python, that's great, but this is certainly explicit. So these are all in nanoamps. So we're just going to run this. And every single time, I'm going to initialize my simulation to -65 millivolts. And I'm going to run it for 10 milliseconds. And then so what I'll do, in order to actually plot this, I'll start out, I'll construct my generic figure. So fig is go.figure. I don't know why it just disappeared there. Fig is go.figure. And then on this, I will just add trace with go.scatter is going to be have x values of t and y values of v. And I'm always recording them. I don't have to change anything. I don't have to do anything extra. But so boom, that's going to be it. I've done my entire parameter sweep. And when I'm done, I'm just going to go ahead and plot it out. And so there we go. We see the values for different things. I neglected to label these things. So what I can do, and this is the other nice advantage of sort of playing around interactively, I can always just go back, as opposed to just running a pure script, I can always go back and make a change if I see I didn't like something. So I didn't like that I didn't name things, so I'll just give it a name. And I'll say that the name is going to be amplitude is equal to whatever ic.amp is. And in Python, that's how you insert values into strings. It's known as an F string. It's like a JavaScript template string. But so now when I mouse over this, I see which curve I'm on. This is the amplitude is 0.3 curve. So 0.3 was enough, 0.2 was not enough to generate that action potential, but 0.3 starts much later. You know, we only peak at time 3 milliseconds versus, you know, as the amplitude increases, we're approaching like 1.6. And so just like that, we've done a parameter sweep. Since I haven't actually shown you this, let me mention. So we've got this thing, this axon. No, we don't have an axon. We have a soma. We've got a soma. It's got Hodgkin-Huxley channels. And inside those Hodgkin-Huxley channels, there are gating variables, right? And the gating variables are things like M, N, and H. And I could also record these as underbar ref underbar M, underbar ref underbar N, underbar ref underbar H, and so forth. And I could do the vector records. But I just want to mention that to make sure that, so this is the syntax to access it. So you find a location, a section, and then you use parentheses to denote which segment, the Hodgkin-Huxley mechanism, and then the variable. All right. Does anybody have any questions on our first parameter sweep in Neuron?
Can you hear me?
Yes.
Yeah, I have a quick question about M, which you just showed there. So you finished the last simulation in that for loop was when the amp was 1.2 nanoamps. So that value for M, is that what M is at the end of that simulation?
Yeah, that's true.
Okay, thanks.
Yeah. And so just for the record, and Bill had a figure that was somewhat similar. Hello. Why is it not letting me type? So if I were to just, if I wanted to see how M varied over time, you could imagine that I could create a vector that records the center of the soma's HH M values over time. And I'll just leave it as the current amplitude because I don't care. But I'll just initialize and I'll continue on to 10 milliseconds, 65 millivolts. And then now that I've done this, I can just do the go.figure, data is go.scatter, x is t, y is m, and I'll show this. And then, so this is how m changed over the course of the simulation. That last one with the amplitude is 1.2. I could just as easily have recorded, n or any other gating variable. How would one be able to import the neuron models in ModelDB to this Python version? So there are two, in ModelDB, you'll find neuron models of two main types. So the first main type is Python stuff, in which case there's nothing to do. So I'm going to assume that you don't mean those. There's another language that you'll find some models in Neuron known as HOC. You'll find these .hoc files. If you do, I'm sorry, that sucks. No, if you do find Hoke files, you can use this h.load file. Let me find it. And we actually, you'll notice if you look at this h.load file, I'm loading a neuron library, which is actually the Hoke library. It's a library that was written in Hoke. So h.load file parentheses whatever file, Hoke file that you found. And so what'll happen then is inside Python, like if I had a Hoke, if you're lucky, you just load everything in and then L as well. If you want to call a specific function, if there was a function, a procedure is what it's called in Hoke. If there was a procedure called setup model or something, then it would be h.setup model inside of Python after you've done the load file. Does that answer your question? Okay. So yeah, so all of this is perfectly happy. You can play around Hoke, Python, they all mix and match and everybody's happy. Hoke can call Python, Python can call Hoke. I am running a bit behind schedule, but I do want to just sort of hit on a couple of points before I pass it over to Adam to talk about reaction diffusion and chemical dynamics. Fundamentally, I'm in a biostatistics department. I care a lot about math. I care a lot about convergence. So if you want to increase accuracy, maybe you want a smaller time step. So by default, Neuron's using 1/40th of a millisecond. You can set this h.dt. You can use variable step control. And if you're using variable step control, what that means is Neuron is not advancing by same amount of time. What Neuron's going to do is it's going to estimate the accuracy. And I'm going to say, I don't want the error at any time step to be above a certain number. So here 10 to the -5. And then it's going to adaptively choose how big of a time step it can make to keep the error constrained. You can also adjust the spatial resolution as well, as we've sort of mentioned. The other thing that I want to mention, there's this great resource called neuromorpho.org, has 151,000 reconstructions from across the brain, hundreds of different model organisms, I'm sure. It's got a bunch of morphology data. Every single one of them is available in what's known as SWC format, which Neuron's perfectly happy reading. Neuron supports a number of other common morphology formats. Importantly, if you're using NeuroLucida, it'll bring in the soma outline, which if you're dealing with 3D simulations of what's going on near the soma, this could be important. So every single entry in Neuromorpho has an SWC version. They also have the original version as the authors provided it, which could be across a huge number of things. They're all associated with publications. They have a tremendous amount of metadata that's associated with them. So this is from one single cell reconstruction. My main caution for you is that people construct these morphologies for a variety of reasons, and they're not necessarily just simulation. So not every morphology was reconstructed to be used for that. They may have amputation, they may have z-axis errors, they may have lots of weird things. Check it out, be aware, look at why this example exists. If it's a reconstruction because somebody took it from a brain of somebody with Alzheimer's and you're not studying Alzheimer's, well, maybe that's not what you want, right? Some tips here. Again, I'll post these slides so I don't feel the need to go into them in detail, but there's some things for you to look at whenever you're working on simulations, as to judge whether or not something is going to be appropriate for your model. Here's code to load in the morphologies. It's a library that was actually originally implemented in a language called Hoke. All this stuff is loaded in through h.load file, but in any case, there's a function, import 3D SWC read, that'll read SWC files. If it's NeuroLucida, import 3D _NeuroLucida 3. And again, this is one of those things where if you're working inside of a Jupyter notebook, it'll auto-complete for you, so you don't actually need to know what exactly it's called when you start typing. It'll hint you the right direction. We've already talked about plotting morphologies. It's one of two main neuron-specific types of graphs. The other one is what's known as a Rangefire plot. And I will post a link in Discord. This is an example of using a Rangefire plot. But what it is it gives you a pseudo line scan. So you'll show you, instead of the membrane potential on a heat map, maybe you want the membrane potential along the path between two locations. And it'll do that for you. And sometimes shape matters, sometimes it doesn't, but there's a ton of cases where the shape do matter. If you want to incorporate specific rules based on, things are physically located near each other, well, okay, well then shape and position matter a lot, right? If you want to look at field potentials or simulating in the extracellular space, or just how do cells live in the extracellular space, that's all there. I will post a link to this. Well, here it is. It's neuron morphology example. So this is an example of using loading in a morphology. I'll post this on Google on the Discord momentarily. And then I'll also post a link to looking at path along the concentrations along a path. And with that, so those two links I'll post on Discord shortly. That's sort of my summary for basic neuron. Does anybody have any questions before I turn it over to Adam Newton to talk about the chemical dynamics? All right, so if not, I thank you for your attention. And I would like to introduce Adam Newton. So Adam's been working with us for, I think, 5 years now. He's got 5 years of experience as a developer for Neuron, and he's been specializing in chemical simulation. So take it away, Adam.
Hi, can you hear me?
Yes.
Great. So yeah, I'm Adam. I'm going to be talking about the reaction diffusion dynamics and how you implement them in Neuron. So this is just an outline of the talk. I'll give some background and motivation, talk about reaction diffusion systems, what they are, and then specifically how you use the RxD module in Neuron to simulate them, going on to talk about the 3D simulations in the extracellular and intracellular space. So neurological issues aren't just network phenomena, although we can get some insight into how the system responds to medicines by looking at upregulated channel activities and that sort of thing. There are also things that happen on a different time scale, things that lead to axon blebbing, loss of myelination, dendritic pruning, amyloid tangles forming, spreading depolarization and stroke. These dynamics can happen inside and outside the cell. So we know that sodium currents raise the membrane potential and potassium currents lower it, but what's a current? A current by definition is movement of charge, and these charges are carried by the sodium potassium ions, but what happens to all of these ions? So there's a pretty simple formula involving Faraday's constant, H dot Faraday in Neuron, for the relationship between a sodium current and the change in concentration. In 1 millisecond, it's 10,000 times the sodium current multiplied by the area and divided by the volume times Faraday's constant. So whether this has a big or small impact in part depends on the volume and the current. The typical sodium current for squid axon is about 10 millimolar. Potassium is about 54.5 millimolar. It's compared to around 125 millimolar in mammals. There's different values that have been found in the literature. And if you're looking at something like calcium, it's then far less. So you're looking at around 100 nanomolar intracellularly. So why is all of this important? The point I'm trying to make is that a neuron is not a transistor. In a transistor, currents go in or out any time of day. You get the same input-output relationship, whereas a neuron has states. These buildup of ions have consequences. So this is just a figure we saw earlier in Bill's talk from the Wikipedia that shows some of the things you have in a neuron. You've got the endoplasmic reticulum, the nucleus, you've got spines, dendrites, synapses. There's a lot going on. So neurons have states and they're affected by the brain state. The suprachiasmatic nuclei is a small region of the brain. It has around 50,000 neurons and their firing rate follows the circadian rhythm. In mammals, it's a heterodimer of the clock and BMAL1 that promotes the expression of their two genes. They dimerize and then inhibit their own activity. So this drives a oscillation in the proteins that then drive an oscillation in the firing rates. Winograd et al. Found that hyperpolarizing certain cells in the prefrontal cortex for around a second could alter the firing rate in a way that would be sustained for tens of seconds. Some cells can sustain excitable waves of elevated intracellular calcium concentrations driven by release from the endoplasmic reticulum. And depleting the endoplasmic reticulum of calcium has been shown to eliminate that phenomena. When we talk about medicines, they bind to receptors or channels, but there's often an indirect cascade of second messenger signals that can have effects elsewhere. In ischemia, you get spreading depolarization, this wave of extracellular potassium. So are there any questions at this point? I see there's something in the chat. No, okay. So now I'll talk about reaction diffusion systems, what they are. So this is the definition from Wikipedia. Reaction diffusion dynamics are a mathematical formalism that explain how concentrations are distributed as a result of chemical reactions. They're spreading out in space as a result of diffusion. Mass action kinetics is the assumption that the rate of a chemical reaction is proportional to the concentration of the reactants. Here, K is called the rate constant. We have conservation of mass. So we always have the same amount of sodium, whether or not it's bound to the chloride, it remains constant. But it's sometimes convenient to ignore that. For example, if you have a degraded protein, you might not want to keep track of all of it. And when would the law of mass action not be applicable? So at the microscale, the justification for these mass action kinetics is that you have a lot of the reactants bouncing around, and when they bump into each other enough times, a reaction happens. And so this is proportional to how much of it you have, but that's only true for a well-mixed system. So every reaction is reversible. So in particular, we don't ever get to the situation of everything being calcium chloride. So we have this forward rate and this reverse rate. And then we have conservation of mass. So enzymes catalyze reactions, allowing them to occur sometimes thousands of times faster. So rather than going from the substrate to the product, we bind an enzyme to the substrate, form this complex, then forms the enzyme and the product. You'll notice that this reaction's not shown as being reversible. In principle, all reactions are, but if the product is removed as it's being produced, or if there's a big energy difference in this step, there would be a reversal rate, but it'd be so small that it's reasonable to ignore it. Are there any questions at this point? Okay. So Michaelis-Menten is one of the best known models of enzyme kinetics. It's very widely used, and experiments often report the rate of the reaction in terms of these Michaelis-Menten parameters rather than the individual rates we saw previously. So by assuming a quasi-steady state equilibrium where the intermediate complex ES doesn't change on the same time scale as the product formation, you can reduce the equation we saw previously to this Michaelis-Menten rate for the reaction that only depends on one state, the amount of substrate, and the total amount of enzyme available, which is incorporated into this Dmax parameter. Km is the Michaelis constant, and it's the concentration where the reaction proceeds at half its maximum rate. So this is a comparison of the Michaelis-Menten and mass action kinetics. You can see that for low concentrations, they're both pretty much the same, but as you increase the amount of substrate to around the point where you reach its half maximal rate here, there's a big divergence between what you get with the Michaelis-Menten reaction versus mass action. And that's because you have a saturation due to the limited amount of enzyme available. Sometimes when a molecule binds to a ligand, it makes it easier for others to bind. This is positive cooperativity. The N is called the Hill coefficient. This comes up a lot in pharmacology. It's used to quantify the functional parameter of a drug or in the relationship between ligand binding and ion channel opening probability. And it's best to think of these as phenomenological models. They can be derived from the mass action kinetics, but where you have molecules simultaneously binding to n sites, but this isn't really physiological, and n is often not an integer, and its value just bound by curve fitting. These show various n's with an amount of substrate. As before, K is the half activation concentration. That was a brief overview of reactions, but they all assumed the reactants were well mixed. So what about space? We know neurons have spatial extent, but ions and protein concentrations, that cellular mechanisms and endoplasmic reticulum, they all vary with where you are in the neuron. Concentrations can affect different locations, either via active transport or diffusion, which brings me on to diffusion, which on the micro scale is the process of random motion, Brownian motion of particles. And on the macro scale, this translates to a net movement down the concentration gradient that's described by Fick's laws. So Fick's first law is that the diffusive flux is proportional to the concentration gradient. And the second law is that the div of this flux gives you the change in concentration phi. This equation should look familiar, because if you change phi, the concentration, to V, the voltage, and choose the correct value of D, this is just how current spreads. So this is just like the cable equation. So where does diffusion occur? Pretty much everywhere. It's in the cytosol, in the organelles, and in the extracellular space. So 100 micrometers is not a particularly long distance, especially for a pyramidal cell. The expected time for a molecule to travel that distance, if its diffusion coefficient is 1 micrometer squared per millisecond, which is the sort of typical order of magnitude you'd expect for some of the ions we're talking about, it would take it 5 seconds for the particle to move that far, which is quite a long time for the timescale of neurons. And this, if you wanted it to move 10 times further, you'd have to wait 100 times longer. So does this mean that diffusion is useless and we're limited to active transport? The answer is no, because you can think of chemical spread as analogous to electrical potential spread. So if there's no active currents, a cell won't carry a signal very effectively. If there's some sort of regenerative dynamics, where the presence of a signal leads to the signal itself getting boosted. So for example, a cell depolarizing leads to sodium channels opening, which further depolarize the cell. In a similar way for reaction diffusion, if you have elevated cyclic calcium, that can lead to IP3 receptors in the ER opening, releasing calcium from the endoplasmic reticulum in this regenerative effect for calcium-induced calcium release. And we'll see a model of that in a bit. So that's it for the background. Are there any questions at this point? Okay. So now I'll talk about reaction diffusion using Neuron's RxD module. I'll start by going over the Python interface, show you how you can use it in your models before giving a few more detailed examples. So there's plenty of information available about the RxD modules. There's the read the docs, the links there for that. And also contact us via the forum or by email if you have particular questions or difficulties. And if you run into a bug, we're on Neuron's on GitHub, so you can submit an issue there. They're very helpful for us. And while it's possible to do everything I'll describe here without using the RxD module, using the module should not only make it far easier to do, far easier to write the model, it should also make it much easier to read and understand the model, which is essential for your model to be useful, for reuse, and to avoid errors. So here is just an example of how with 2 lines, you can declare a region and a species on that region. And by default, Neuron only has 2 domains for the chemical concentration, but RxD allows you to add arbitrarily many domains. So RxD has a simple Python interface. So whatever you're modeling, you'll follow these 3 basic steps declaring where the dynamics occur. So for example, the cytosol, who are the reactants involved. So for example, the calcium, and what happens to them. So the reactions may be buffer. And you follow the same basic process, whether it's deterministic or stochastic, whether it's in 1D or whether it's in 3D. So RxD supports a rich and customizable set of geometries, including very simple ones like inside or membrane, as well as more complex ones like shells for radial diffusion, fractional volume. We recently added a multi-geometry region where a region can have more than one geometry for different sections. So for example, if you wanted to define a dendrite with shells and then attach a spine with just inside the outer shell of the dendrite, you could do that using the multi-geometry region. If you want your concentrations to interact with N-modal, with the rest of Neuron, you need to give your region an NRN region. So for typically I for intracellular, sometimes O for outside the cell. To declare a region, you need to tell it what sections to use. So h.allsec, or you can use a list to filter for particular sections. For specifying for specifying your reactants, you need to tell it the region involved, and you can give it a diffusion coefficient. And if you import some neurons, some units from Neuron, as Robert was showing you earlier, you can specify the units for your diffusion coefficient. You should specify an initial value, typically in millimolar. And you should give it a charge, especially for, it's important if the species is going to cross the membrane, either for RxD to work out from the charge how much, what concentration change there should be, or if you have a multi-compartment reaction, I'll talk about later, if you have a reaction where the species moves across the region, you need the charge to work out how big a current that reaction should generate. It's also important for calcium, sodium, and potassium, which are known to neuron. If you're going to use that name on a region that neuron cares about, that they have the correct charge. So neuron's variable step solver has a given error tolerance. It defaults to 10 to the -3, which is fine for membrane potential in millivolts, or something like potassium, where you have around 125 millimolars of it. But it's not really appropriate for something like calcium, where you typically have 100 nanomolars. So rather than changing the tolerance for your entire model, you can change it for a particular species. So here, for example, with calcium, you can set atoll scale to the nanomolar range, so it will keep closer track of differences in calcium. So your initial values can be functions of the node. RxD uses nodes for all of its concentrations. And here is a function that takes the node and looks at its distance from the soma, and then returns this hyperbolic tangent to sort of step function, approximation of the continuous step function for that distance for the IP3 concentration initial conditions. Another example, you could use the node's 3D location instead of its distance from the soma, or really any property of the node, so what section or region it's in, to define the initial concentrations. Parameters are similar to RxD states, which are like species but don't diffuse. The difference with a parameter is RxD won't ever change the value of it. They're useful if you have a value in your reaction that varies in time, space, or across simulations. If it's just going to be constant everywhere, you could just use a number. But so, for example, you might want to limit a reaction to a specific section, for example, the spine head. So in that case, you would set your initial value to a function of the node that was 1 when it was in the spine head and 0 everywhere else. And that way you could limit your reaction. So there's this handy shorthand where for defining parameters, so you pass in the parameters with their initial values, again using neuron units. So the default is for millimoles per millisecond. So it's quite handy to have these units to work out nanomoles per hour for you. You pass those in and they're just added to the global environment. And so this in particular is used for this model of, I think, protodynamics for fly circadian rhythm, which is available, one of the tutorials, and it's available at this URL here. So are there any questions at this point? Check the, nope, okay. So specifying the then what, your reactions.
So Adam, there was actually a question.
Oh, I missed
so
it.
I guess the motivation of all of this, or where this is going. I don't know. Does somebody want to put?
So the idea is to be able to model reaction diffusion systems in Neuron. The advantage of being able to do this in Neuron is you can then link them to what Neuron already does very well, which is the electrophysiology of neurons and networks of neurons.
So can you give maybe a few biological examples as to when this comes up?
So I'm getting on to a couple. So there's the calcium-induced calcium release that I hinted at earlier. I'll show a model of that in a second. We have a model of spreading depolarization. So when a neuron depolarizes, it releases potassium into the extracellular space. If you have a big enough amount of extracellular potassium, this can trigger further depolarization, and you get this regenerating wave of spreading depolarization. So it's a couple of examples.
Could I interject something? The general idea is that, not surprisingly, the neuron is a very complicated piece of machinery. And there's actually a very cool paper, which I think is wrong, about the neuron in the neuron, which is this idea that maybe the endoplasmic reticulum is electrically excitable, something that's never been shown, but on the other hand has never been shown to not be true. And that would give very rapid signaling within the neuron to different parts of the neuron, which would solve a bunch of mysteries. Now, even in the absence of that, something that Adam's going to show is this calcium-induced calcium release dependent on the endoplasmic reticulum, which would allow the same sort of effect of communication between parts of the neuron that is not mediated by the main cell membrane. So the best we can unfortunately say is that there's a lot of unknowns about how the neuron communicates with itself. And this is one of the hypotheses that may help us understand it. Certainly, again, I recommend Rama Blackwell's paper, which is called Calcium, the Answer to Everything. It's not 42, it's calcium. And this idea that calcium is doing all kinds of remarkable signaling, it's still very mysterious within the cell.
Thanks. And I see another question. How does RxD handle interactions of free-floating species with pumps in the membrane, etc.? Is that not possible? It has to be well mixed. So the way we handle it is by discretizing space and assuming that within each compartment, we can assume that the compartment is well mixed. And you can specify pumps and things in the membrane, either with n-modal mechanisms or multi-compartment reactions, which I'll get onto in a little bit.
And so just to say, so what that means in particular is that everything that you do with the mod files plays nice with RxD, and the mod files can see whatever's calculated using the reaction diffusion stuff.
Yep, I think that's a good point. So reactions, we have this simple calcium buffering. The mass action kinetics are shown here, and how you implement that in RxD is shown below it, with just specifying a reaction with your calcium and your buffer, going to your calcium buffer, these forward and reverse rates. For repeated reactions, so if you have 2 hydrogen and an oxygen, you can just do ×2. And for arbitrary reaction formula, like the Hill dynamics we showed earlier, by setting this keyword argument mass action to false, you can then specify your rate directly. And so we have that just here. So multi-compartment reaction and rates first. So a rate is useful if you just have one species involved. So here IP3 degradation, it's IP3 is removed at a rate K multiplied by the amount of IP3 you have. For multi-compartment reactions are useful if you have a reaction that crosses some membrane. So you have to define the membrane. That's will be a separate RxD.region. And then you have here calcium in another region, the ER, that we have to find somewhere, and the calcium in another region, the cytosol. And you have a movement between the two with this forward rate and this reverse rate. For multi-compartment reactions, the rates are in terms of molecules per micrometer squared per millisecond, and the micrometer squared depends on the membrane area. So accessing values in RxD is done primarily via the nodes. Species or species on a region provide a list of nodes that can be filtered by various criteria, so section, segment, the region, etc. And you can record values from these nodes as in a very similar way to recording values from neuron that Robert was showing earlier with a ref concentration or a ref value. You can also set the concentrations in the node. So as an example, where we're just doubling all of the values, doubling all of the concentrations. If you do this and you're using variable step integrator, you might need to call CVOD reinit. Or if you're in fixed step, you might need to call species underscore transfer to legacy to update the values in neuron itself. And nodes give you other features like the surface area or volume and the position, its relative position and section. the primary way of accessing RxD values. So as I was saying, to record a concentration, you do that via a node. This is a node list, but because there's only one element in the list, we can also treat it as a node. We don't have to access the 0th element. And ref concentration or ref value is then something we can just pass into a vector to record it. We can use these same references with the Neuron GUI for plotting things. So now I'll give a little example collab of calcium buffering. Right, so this is, I just run everything to start with. So this is a collab that I prepared earlier with just to start with just a very simple pedagogical example of calcium buffering, where we're going to go through how you use the RxD interface. So we're just going to take 2 calcium and a buffer. They will go to buffered calcium, and the buffer will be degraded. So to start with, we need to install Neuron, as we're in a collab environment. If you're running it locally, you wouldn't. Robert was showing that earlier. Then we need to import H for the regular Neuron stuff and RxD for the reaction diffusion part of it. And then a bunch of units that are going to come in handy later. And we'll also import some stuff for plotting and standard run for hope for H continue run to run the model. So then we're on to the actual RxD stuff, which then just follows this simple formula where the reaction takes place. So we define a section, and then we define a region of that section. We give it a name for the cytosol. It's not important for this model, but we specify NRN region I. So if we had mechanisms that used calcium, the calcium would be linked to this. You had mechanisms, they would be linked to this region, and we give it a geometry just inside. So then we specify calcium that's on the cytosol, give it a name, we give it a charge because neurons are aware of calcium, and so it needs to have the correct charge. And again, if there were mechanisms, currents would need to know how to scale it to get the concentrations. We give it an initial concentration of 60 nanomolars. Our buffer.
Hey, Adam, I'm sorry. Could you post the link to this in the chat? So sorry to interrupt, but somebody asked.
Okay. So the buffer and the calcium buffer, who's involved. Then we have what, which is our reactions. So 2 calcium and a buffer go to buffered calcium. This is the forward rate, reverse rate's a lot smaller. And we have degradation of the buffer. We set up stuff to record things, which is pretty standard. We can, because we've linked the calcium to Neuron's definition of calcium, we can record it directly with ref CAI, because buffer and CA buffer aren't relevant for the rest of neuron. We record those from the nodes. So this is giving us a node. Again, as we only have one node, we can record directly from it. Then we initialize and run as normal, and we plot a figure showing the results. So we have calcium dropping as it becomes buffered, and then the buffer slowly degrading, and the calcium gradually returning towards baseline. That's a very simple model. You wouldn't really need to use Neuron for it. It doesn't really have any of the electrophysiological features. So next, I'm going to delete the model and next talk about this calcium-induced calcium release model. So this figure here, we have two regions, the cytosol and the endoplasmic reticulum, and we have three mechanisms linking the two. So we have the Circa pump, flux is defined here, where it removes calcium from the cytosol and puts it into the endoplasmic reticulum. That's why there's a minus sign here. We have a leak, which allows calcium to leak out of the endoplasmic reticulum into the cytosol. And we have this IP3 receptor, which takes IP3, it was gated by IP3, which is the M gate here, and by calcium here in the cytosol. And so when they're present, it will open and release calcium from the cytosol, from the endoplasmic reticulum into the cytosol. And this term here is just a scaling for the area of the membrane. So these three fluxes taken together with diffusion define how our cytosolic and endoplasmic reticulum concentration would change, along with IP3, which is also diffusing. So this model, available on ModelDB from a 2015 paper, takes this these calcium dynamics together with some calcium channels, passive leak, some potassium and sodium channels, and an AMPA receptor, puts them all in a dendrite. What we're going to look at is the effect of stimulating the AMPA receptor before releasing IP3 into the dendrite, and see what effect that has on the calcium wave. So first, we just need to download the n-modal mechanisms, compile and load them. So this grabs the model from ModelDB's Git and compiles the mechanisms for us and then loads them into Neuron. We're going to use variable step integrator, so we just set that to active here and change the temperature to something more mammalian. Then this block of code, it's doing all of the classic neuron electrophysiology. We're creating two dendrites, and then for each dendrite, we're saying length, end-seg, diameter, axial resistance. We're putting in all of the mechanisms that were in the paper and shown in that figure up there, and then we're setting mostly the conductances for all of these mechanisms. Now, dendrite A is going to receive a lot of AMPA stimulation, and dendrite B isn't. So we only add the synapse to dendrite A. We put that in the center of the dendrite. We create a net stim to give it 200 pulses at 50 hertz. And then we connect the stimulation to the synapse and set it to active. So then we get back to the RxD model. So we specify, again, it's where, this should be who, but start with where we have the cytosol. Here we're using, it's the same as before, but we're using a fractional volume geometry. So it's 83% of the volume is occupied by the cytosol, but all of the surface is occupied by the cytosol. We define the endoplasmic reticulum, which takes up the other 17% of the fractional volume. And for our mechanisms between the two, we need a membrane. So we have the cytosol ER membrane here, which we define as just a border between the two. So then it should be who here, and we've got calcium and IP3. So calcium is on both the cytosol and the ER, This is its diffusion coefficient, has the correct charge. And as I was showing earlier, the initial value can be a function of the node. Here I've called it ND. So we're set that to 100 nanomolar if we're in the cytosol. Otherwise, it's 9.5 micromolar for the ER. And again, I've set atoll scale to micromolar to keep better track of it. The IP3, we initially don't have any, so the initial is 0, and it has a larger diffusion coefficient. So then we come to what, which is our reactions, and these are the a gating variable for the IP3 receptor, and then just the 3 multi-compartment reactions for the that I showed earlier in the figure. So we have the IP3 moving calcium from the ER to the cytosol. We have the Circa pump, which moves from calcium from the cytosol to the ER. We have a leak passively going both ways, depending on the concentrations. So we're going to add an IP3 stimulus. So we're going to make this an event. So this is a function that will give us a function that for the middle of the dendrite, between sort of 48 and 52% of the way along the dendrite, it will set the concentration to conc. Otherwise, it will leave it unchanged. And after changing it, we need to do CVOD reinit. This is just our standard recording things. We want to record the voltages, the cytosolic calcium, and then the calcium in the ER, for which we need the node list. But again, because we've specified a segment and a region, we're down to just one node, so we can treat the node list like a node. Then we initialize and run our model. We add this event at 4.5 seconds. We're going to increase IP3 in the center of the dendrite to 2.5 millimolars. And we're also going to, every 60 milliseconds, record the cytosol in both the calcium and the ER, just save that as a big NumPy array. So then we run that and plot the results, which hasn't shown up. Oh dear. So I think that might take a few seconds. So I think, are there any questions at this point? If not, I'll continue with the slides and come back to that in a sec. So here is an example from another paper where it takes the same model I was just showing you and puts it in a network context together with the addition of hyperpolarizing activated HCN channels. It has 776 neurons and produces persistent network activity via this current excitation and inhibition. It also has a metabolic glutamate receptor, which produces IP3 in response to synaptic stimulation, which supports the calcium-induced calcium release model we were just looking at, and also shifts the activation of HCN channels, which help provide support for continued network activity. Shown here is the firing rate discrimination. It's the ratio of the firing rate for neurons that were in a stimulated set and against those that were in an unstimulated set. And it's a way of quantifying how well the network encodes a pattern. So this model then looks at the effects of the initial calcium stored in the endoplasmic reticulum and the voltage-gated calcium channel density. And so this shows an inverted U relationship along the x-axis, where at low levels of voltage-gated calcium channels, calcium influx increases post-stimulus firing, but at higher levels, it will increase the firing in both the stimulated and unstimulated populations, leading to this poorer firing rate discrimination. Calcium stores, as they get larger, it always improves the firing rate discrimination because they really only contribute to the the stimulated cells firing. So moving around, this shows the plots of the two firing rates of the two different sets at the corners of this plot. So at D, it doesn't have any initial ER calcium and no voltage-gated calcium channels, and so there's no difference. It does very badly. Then moving around to E, where you increase the voltage-gated calcium channel density, both populations firing rates fire a little better. You get weak suppression of the unstimulated population, so it does better, but still not very well. Then with high voltage-gated calcium channel density and high ER scores, that's C shown here, you do very well, reasonably well, but because the voltage-gated calcium channels are enough to boost the firing of the unstimulated population, it doesn't do as well as B, where you just have no voltage-gated calcium channels, but a large ER store. So you get the biggest difference there. So are there any questions? Okay. So now consider 3D reaction diffusion in neurons, starting with the extracellular space. There's a lot going on in the ECS that you might want to model. Got neuromodulators, acetylcholine, dopamine, adenosine. A lot of drugs act in the brain via the ECS, and pathological conditions like spreading depolarization and ischemia, or amyloid beta formation in Alzheimer's disease also act by the extracellular space. So at the microscale, the ECS is composed of sheets and tunnels. They're about 10 to 30 nanometers wide. They're shown in this corrected reconstruction of EM slice. We're not often interested in that fine scale structure, although there's work like the recent Lytton paper where they reconstruct a fragment of brain tissue, where this may be the scale you want to use, and then you have to deal with the EM artifacts. But for most of what we do, where a coarse-grained volume average approximation is more appropriate, where the diffusion characteristics of the tissue are the tortuosity, the proportional increase in path length to avoid obstacles, and the porosity or volume fraction, the amount of free volume particles have to diffuse in. A nice thing about this approximation is that these values can be found experimentally. This is a schematic of a setup where with ion phoresis, you put this charged molecule that's not taken up by cells very well into the extracellular tissue, and then a short distance away, you measure the concentration, you get these curves, which you can then fit with the diffusion equation, and you can use those to extract two parameters. So in normal conditions, about 20% of the brain tissue is free volume. The tortuosity is about 1.6. In anoxia, you have the cells swelling. It reduces to about 5% free volume, and the tortuosity increases to about 2. So in terms of RxD, extracellular is just another region for the Python interface. You'd say RxD extracellular, you specify bounding box, X low, X high, so on, and as well as the voxel size and these two diffusion characteristics that I mentioned, which could be constants or functions of location, or more recently with dynamic diffusion characteristics, they could be RxD states. We support anisotropic and heterogeneous diffusion characteristics. So D can be a tuple of values for the different X, Y, and Z directions. And by default, we use Neumann or zero flux boundary conditions, but this additional keyword argument, use that to set the values, set Dirichlet boundary conditions so that set the value directly at the boundaries. So 3D simulation supports multi-threading just through this RxD n threads command, and we get reasonably good speed up. That speed up to about 2/3 by the number of threads for ECS and about a half for ICS, as long as the models are big enough. So now I'll try and run through an extracellular tutorial. Let's see if I can copy that to the chat. Still not come up, but so this is just, oh, sorry.
May I ask a question?
Oh, go ahead. Yeah.
Yeah, is it fine?
Yes, please do.
Oh, okay. So before switching to this extracellular tutorial, I just wanted to ask one question. So as far as I understood, with these diffusion equations, you are trying to estimate or compute the calcium concentration or other ions of interest at some points on the neuron membrane. Yes, am I right? For example, the soma or the cytoplasm.
Yep. Yeah.
Okay, now I have one question. So if we want to apply this to this implementation of your code to synapses, so for example, NMDA synapse or AMPA, so there we have different subunits, and there are these chemical reactions happening of binding glutamates neurotransmitter to these subunits, and then they open, then sodium calcium goes in, something like that. So what I mean, can we also apply this in brief in your method to synapses, single synapses?
I believe so. There might be issues with modeling it stochastically, which we're still trying to support fully in RxD, but I think in principle you could use the same sort of species and rates and multi-compartment reactions to do that sort of thing.
So
we actually made that a major aim of the current round of the RxD grant. So we are very interested in that and would love help if anyone wants to offer. One of the difficulties there is that we need to do, ideally, what we need to do and what we can do may be two different things. Ideally, we would like to do presynaptic intracellular reaction diffusion to know something about the release of vesicles and the mechanism of how that works through a second set of second messengers, a cascade. Then we need to do the cleft, which is very tiny extracellular diffusion, so may need a mechanism that we're not currently using for extracellular diffusion because of just the scale is different. And then postsynaptic activation with activation of NVA, activation of AMPA, some second messengers that are involved there. One of the interesting results from some recent synaptic papers, which unfortunately I can't cite, so I'm not maybe getting this quite right, is this question of whether NMDA activation somehow actually triggers new protein synthesis way down in the soma. And this has to do with what I was saying before about the interaction across parts of the cell that is necessarily not using the primary plasma membrane, because that's used for all this other signaling. So you have this intracellular signaling that's somehow going on. Another related topic is synaptic tagging and capture. If you're going to activate a synapse and cause LTP, long-term potentiation at that synapse, then you're going to need to insert new proteins. So as the ribosomes and as the mRNA and perhaps as even proteins are coming up, being sent up the, let's say, a main dendrite, how do they know which synapse to go to so that they don't activate the wrong synapse? So it is a tremendous complexity of activity, of course, associated with the synapse that we've just started to do. In fact, Adam's been working on something looking at PKM zeta and how you can get spillover from one synapse to another, from one spine to another, due of LTP due to the actions of that molecule. It's a very fascinating topic.
I see. Thank you so much. Now it is very clear. Yes, I see the point. Thank you.
Thanks. So I'll try and run through this bit quite quickly as in short time, but it's very similar to before. Installing Neuron, grabbing a couple of files. There's a mechanism that gives me a constant source of potassium for this example, and this is a morphology file from NeuroMorpho. I compile the mechanism, import neuron and some units as before, set in the number of threads, which I talked about as pretty straightforward. I create a cell class. This class is just going to load the morphology and input the mechanism, which is a constant source of potassium, and give me a bounding box for the cell. Then I create the cell using the morphology I downloaded, define the extracellular space using the bounding box of the cell with some additional padding. Here I'm using non-cubic voxels, so they're 20 by 50. And I specify the volume fraction and tortuosity to the physiological values you'd expect. I'm defining potassium on this region with initial concentration of 3 millimolars and the boundary condition 3 millimolars. And then I have this script for animating the diffusion in the extracellular space. The important neuron bits are, I'm just initializing here, then I'm grabbing the species, so in this case, potassium. States 3D is a way of getting all of the extracellular 3D states, and I'm taking an average over the Z direct over the depth so that I can plot that in 2D. So this shows just the diffusion in the extracellular space of a constant source of potassium from the morphology file I downloaded. As I mentioned, everything in RxD is all of the values are done via the nodes, and the species on extracellular here has some additional mechanisms for getting nodes, so I can get them by their extracellular location. So here at the origin, where I can get them by their IJK values in the grid. So this is fairly far away from where the cell is. So I'm just going to record those two values and plot them. And you can see the one that's should have labeled, put the axes up, but this is the one near the cell, it increases quickly, and the one far from the cell increases slowly. This is boundary conditions. I think I already had that. Extracellular reactions proceed very much as the reactions we've seen so far. So this is an example of potassium buffering by astrocytes, treating the astrocytes as sort of a field in the extracellular space. So I have a reverse rate and then a forward rate defined by this threshold and this equation. It's important to note you can use most of the maths, all of the maths functions with RxD species, but you have to get them from RxD math. So here it's just the exponential of the difference between extracellular potassium and this threshold divided by 1.15. And so with the example with buffering is that the concentrations end up being orders of magnitude lower because so much of it is buffered by the astrocytes. Finally, just mention that you can have anisotropic diffusion, and the way you do that is by defining a tuple of 3 different diffusion coefficients. So here it diffuses in XY direction, but not in the Z direction. So now go back to the slides. So here's a nice video from one of our models of spreading depolarization. The white dots represent neurons. There's an initial sphere of extracellular potassium that causes the neurons to depolarize, releasing more potassium, forming a positive feedback loop leading. Oh, there we go. Am I not showing my screen? You can see it now?
Yes, sorry.
Oh, that's good. So that leads to this wave of spreading depolarization. So that's it for the extracellular space. Are there any further questions on that bit? If not, I'll talk about intracellular 3D reactions with RxD. So you might be interested in a system where a 1D approximation isn't appropriate, or you may just want to confirm that a 1D approximation is appropriate. So I'll give some examples here of where having a 3D reaction diffusion has an effect. It's very easy to specify using 3D reaction diffusion with RxD. You just need this one line or set solve type. And another useful function you have is for plotting values to grid, give you a dense grid of the values with not a number where you don't have any voxels. I'll just say that it's implemented very similarly to the extracellular 3D using the Douglas-Gunnar ADI, and I've already mentioned that you have multi-threading available. There's this example of a regenerative wave. Robert, do you think I should run through it or just skip it and people can look at it at their leisure?
I'll post this link to Discord and to the chat, just in the interest of time, so people can have a little bit of a break before we move on to the next section. So I will post this link momentarily.
Yep, and that's it's an example of the scalar bistable wave, showing that in 3D you get this curvature when the wave enters from a thin section into a thicker section, and it just goes through some of the functions you'd need to plot that. And this other example on is shows wave curvature delays at the soma. It's similar to this example in our tutorials. So you can also have a look at our tutorials when you have the chance. And this 3D stuff works with all of the other stuff in Neuron. So for example, this is a point process that's been put into a cylindrical bit of dendrite. It just shows the concentration spreading out over time. And it just shows plots at a different distance from the source and how the concentration builds up and then diffuses away. So finally, these are some further sources for information. We have papers on this. The Neuron Forum is an excellent resource if you have any questions or you don't know where to start. There's the programmer's reference. There's the tutorials I've already mentioned, which are a good resource. Neuron's also on GitHub. If you run into problems, if you think you found a bug, please do let us know. It's very useful to have. And that's all I have. So if there are any questions, otherwise you can get some lunch.
So there's a question on the Zoom chat.
So is it correct to say that non-RxD neurons, the angle at which the two sections are connected has no influence on the current flow, while in 3D RxD, or even simple RxD, the angle of connection matters due to diffusion? RxD, I don't think will affect the current, won't affect the current flow directly, but for diffusion in 3D, the angle matters. I don't think it matters in 1D.
But I agree with that statement, but I will point out that you can certainly make models that depend on geometry in specific ways of how you set up the synapses. Maybe you set up synapses such that they're near something, or orthoptic coupling, or any of a number of reasons that you might care about things. So it's a solid correct but. Yes, but.
Yep, thanks.
Okay, so if one last call for questions. All right, if there are no other questions, so we're going to take a break. Salvador, are you here?
Yes.
So on the schedule, we're scheduled to start at 1:30. Do you want to stick with that, or do you want to push it back 9 minutes?
I think 1:30 probably, so people who are not here don't get confused.
That's a good point. Okay, so in that case, we will resume in 20 minutes. Thanks everybody for your participation, and we'll talk, Salvador will talk about networks and NetPyNE coming up soon. Thank you.
So thanks everyone for attending, and we're going to continue in the second part of this tutorial. Now we're going to be looking at NetPyNE and building networks. So this is the schedule for this afternoon. We're going to do like a short introduction, just 20 minutes. Then Joe Graham is going to go over 3 different tutorials using the graphical user interface of NetPyNE. We're going to have a 10-minute coffee break, and then we're going to go on to the last part where I will do a programmatic tutorial, coding-based, using a Google Colab, and looking at oscillations on a simple network. So importantly, the link here shown at the bottom is a link to these slides. So that might be useful if you want to follow along, and it also has the step-by-step instructions to go through the GUI tutorials. So if you want to go to this address, it's bit.ly/CNS21 NetPyNE. I'll show the link a couple times more. So I'm briefly going to give an introduction and motivation of why we developed the NetPyNE tool. So the brain, as you know, has many different scales, and these scales are nested within each other. So we have the molecular scale with, for example, channels and synapses, building into the cellular scale, circuits, systems and regions, and even behavior at some level. So all these scales are related to each other and affect each other, and that's what makes, or one of the reasons that the brain is so complicated to understand. And so something that we can use to try to unravel this complexity is computational modeling. And in particular, as you have seen this morning as well, the Neuron simulator allows to model all these different scales from the molecular to the cell level to the circuit. And it's the most widely used multi-scale simulator nowadays. It actually allows to build these quite complex and detailed models, such as the one developed by the Human Brain Project, simulating somatosensory cortex, or by the Allen Brain Institute, simulating visual cortex. However, it is quite complicated in some cases to integrate all the information that you require to build these models, from the single cell morphologies and biophysics to connectivity and so on. And so what we wanted to do is develop a tool that builds on top of the Neuron simulator and facilitates the incorporation of or integration of all this experimental data at the different multiple scales, from molecular, cellular to network. And we wanted to do this in a way that made it easy to separate the actual parameters, biological parameters of the model that we're building from the actual implementation in code. So the Python code that you use to build, for example, these neural models we're seeing this morning, looks like this in the right-hand side. And we wanted to shift to a more declarative format. So something that focuses on providing the biological parameters and where the user doesn't have to worry about the actual code implementation. So this has some advantages in terms of standardizing the actual format for definition of the models, which can make it easier to read and interpret other models, as well as to edit existing models, share them across the community, and so on. One of the other motivations was to facilitate model parallelization, so making it easier to run these very large-scale simulations on supercomputers, for example, as well as running batches of simulations where you explore different parameters. And this is possible in Neuron, of course, but it's not always straightforward. You have to take care of distributing the cells in different nodes, gathering back the information. So we wanted this tool to also facilitate this step. And so we have developed this package called NetPyNE, which stands for Networks Using Python and Neuron. And it essentially facilitates all these different steps, from the development of the neuron, of the network models, to the parallel simulation, optimization of parameters, and analysis of the output of these simulations. It builds on top of the Neuron simulator, as I mentioned before. And before I continue, I just wanted to ask everyone who's going to follow along the tutorial to try to load this website. So that's netpyne.org/GUI. And this is how we're going to follow the graphical user interface tutorial. So it takes sometimes a few seconds or minutes to load up. So I just wanted everyone to just log in there right now, so that it's ready in 15 minutes or so when we actually start running the tutorial. So if you open this website and it doesn't work for you, please let us know in the chat or via the other forum. Notion forum is called, I think. Okay, and again, this is the link to these slides where you can find all the other links. So that's bit.ly CNS21 NetPyNE. So I'll continue now the presentation. So as I was saying, we developed this tool, and just to clarify the relationship between NetPyNE and Neuron, here we have Neuron sort of at the bottom level, and this is an example code of how you would create a connection in Neuron. So the NetPyNE tool sits above Neuron, and it's sort of a high-level interface, Python interface to Neuron, which allows you, for example, to define these high-level connectivity rules, where you specify the parameters of a specific connection, for example, connecting a sensory population to a motor population with a probability of connection of 0.5, a weight strength of 0.01, and a delay of 5. And so NetPyNE would take care of creating all the neuron connections corresponding to this connectivity rule in the background, as well as of running the model afterwards, and again, providing different functions for analyzing and plotting the results. And the third step we have, the third level, is this NetPyNE graphical user interface, where you can actually do all the programmatic stuff you do in normal NetPyNE using a graphical interface. You can, for example, create these connectivity rules from a graphical interface and then run the simulations in the GUI as well. Okay, so this is an overview of NetPyNE. I'm not going to go into too much detail, but we have sort of different steps here, what we call the high-level specifications, which is the first step, where the user provides the biological parameters of the network, as well as some simulation options, like how long do you want to run the simulation and things like that. You can import existing models, existing neuron cell models, so that you don't have to define them from scratch in NetPyNE. Then you're able to instantiate the network, so create all of the cells and connections, all of the neuron objects required to simulate this network you have defined, and that is done automatically. And the next step would be to run the parallel simulation. And again, NetPyNE would take care of that step. And finally, you can analyze and save the results to different formats like NeuroMel and Sonata, and run different visualization functions. You also have up here the batch simulation module, which takes care of running multiple of these simulations at a time to, for example, explore different parameters. So as I said, NetPyNE has this high-level language or high-level specification language, which is standardized and is in a declarative format, meaning that it's just a JSON-like format with lists and dictionaries, standard Python lists and dictionaries, where you can define all the aspects of the model, from the different populations and the volume they occupy, to different cell properties, synapses, different types of stimulation in the network, as well as connectivity and simulation options. This is an example of how the different components are defined. As you see, they're just Python lists and dictionaries. And then at the end of this, you would have a single command to run and create and simulate the network. So we will see examples of this in the tutorial later on. An important aspect is that NetPyNE supports the use of RxD, molecular reaction diffusion. So things that Robert was showing this morning and Adam, they are also possible within the NetPyNE structure. And that allows you to link these molecular level phenomena to the network activity. So for example, things like phosphorylation, buffering, second messenger cascades, they can all be linked to the effects they would have on the network firing rates, plasticity, and so on, as well as the other direction. Of course, network level effects also affect the molecular level. And NetPyNE is strongly built on the idea to facilitate connectivity. So we have these very flexible connectivity rules where you can implement things like probabilistic, convergent, or divergent connectivity, as well as custom connectivity. Parameters such as probability or weight that that depend on properties of the cells. So you can have a weight that depends on the location of different cells, or a delay that depends on the distance between two cells. All those things are built into NetPyNE and are very easy to implement. And we have different learning mechanisms, as well as support for gap junctions. These are quick overview examples of some of the analysis functions that are built into NetPyNE, showing different representations of the connectivity of the network, as well as voltage traces, network raster plot, and firing statistics. And an important feature is the ability to record local field potentials. So you can place these simulated LFP electrodes anywhere in the 3D volume tissue that you're simulating, and then record these extracellular potentials. Of course, it's quite useful to compare to experimental data, as this kind of data is quite common in experiments. And here we see an example for a single cell as well as for a network. And we have recently added the ability to calculate current source density plots. So these are obtained from the LFP signals, are the second derivative, and they're also very common in experimental literature. So it's useful to be able to obtain these plots to compare to experimental data. Finally, another important feature is this idea of parameter exploration or parameter optimization, where you're modifying the parameters of the model to match some experimental data or to explore some phenomena. And NetPyNE has several built-in functions to facilitate this process, where you can specify the range of parameters you want to explore and then visualize the results easily, as well as submit to different types of supercomputers and multi-core systems. Here I'm showing the NetPyNE GUI, an example of some visualization of some plots that we're going to see today. And the GUI, of course, allows you to do all the things that you can do programmatically. I think it's quite useful actually for students and beginners who are learning to use the tool, because it allows you to see all the different properties and features that NetPyNE has at a glance and just exploring it. It allows also to save any model that you build in the GUI. You can then save it as a Python script, so you can continue using it later on and do more complicated stuff. And you can also explore and visualize existing models in NetPyNE. So that can be quite useful to get an intuitive interpretation of the models. We are working together with the open source Brain platform to integrate the NetPyNE GUI, and it's practically ready now. So this will allow you to have your own workspace. So this means that you have a sort of permanent online space where you can save your files and work on some project and then come back the next day and continue working on that. And so you have your workspace hosted on open source Brain. And you can then from there run the NetPyNE GUI and build your models, run simulations, and again interact with your own file system, as well as with, for example, GitHub repositories, so to export and import from GitHub, and so on. So here's just some visualizations run within open source Brain. And that is a nice feature, because then open source Brain also has other built-in tools, such as this NWB Explorer, which allows you to visualize experimental data. So it will be possible at some point to export the data from your simulation in NetPyNE within the open source Brain platform and export it to be visualized within the NWB Explorer, where you can compare directly to some experimental data sets that you have available. So this links within a single platform, the modeling and the experiment visualization tools. We are also now working with the eBrains, the Human Brain Project eBrains platform, and NetPyNE is also available now there to run as Jupyter notebooks, where you can run the simulations of different NetPyNE models. And as well, the NetPyNE GUI will be available via eBrains. And we're working to integrate it with the eBrains file system as well, so you can also save and load files from your own account in eBrains. Just a shout out to Metacell, which is this company which develops software for neuroscience, and they have developed both the open source Brain platform as well as the NetPyNE GUI, and they've done a fantastic job. Finally, I just wanted to mention some features in terms of compatibility and exporting to other formats. So NetPyNE can export and import to Sonata and the NeurML standard formats. So this allows you to read models from other simulators, as well as export to a standard format that other simulators can also read. Here's an example using the Sonata format to read the same model in the Allen Brain simulator as well as NetPyNE and getting the same results. And to end, here's the NetPyNE website, netpyne.org. And here you can find lots of documentation, tutorials, links to Jupyter Notebook tutorials, to the YouTube channel. And so there's a lot of information to learn and practice with the tool. We have Q&A forums as well, where there's a lot of different questions you can check. Our publication of NetPyNE is published in eLife, if you want to know more details. And finally, I just wanted to mention the list of NetPyNE existing models that we know of. We have a link here at netpyne.org/models with a list of the different models, the developers, and some links. So if you are interested in building a model in NetPyNE, I would recommend starting here and checking if there's any existing implementation that you can reuse. We're lucky that the community is growing quite quickly, and we have many different labs or people from different labs using and building models of many different parts of the brain, different parts of cortex, thalamus, cerebellum, even heart myocytes, different phenomena and disease like ischemia or epilepsy, as well as different stimulation protocols like TMS or TDCS. And to end, I just very briefly wanted to show a couple of example models built in NetPyNE. So this is a model of motor cortex microcircuits, very detailed in terms of the different cell types that we built in, the different connectivity at multiple scales, from dendritic distribution of synapses to local circuitry to inputs from other parts of the brain. So it's around 10,000 neurons and has 30 million synapses. Similarly, we have developed a model of macaque auditory thalamocortical circuits. So this also includes a lot of detail in terms of different cell types, 4 different excitatory cell types, 4 different inhibitory cell types, thalamic cell types, similar amount of neurons, 12,000 neurons and 30 million synapses, and we're reproducing data from macaque. And very recently, we have completed the development of this thalamocortical sensoromotor cortex model, which is based on the Blue Brain project model from 2015, and it's now available in NetPyNE. It's a model of mouse S1 or rat S1, again with 30,000 neurons and many different cell types. So now this is will soon be available for you to run, and this is a recent simulation. We have extended the model by including also thalamus, which is this activity which you see at the bottom. So now we have S1 connected to the corresponding thalamic circuits, and this will be publicly available for people to use. One last example is this recent model we converted from NEST, the Podgens and Disman, a pretty well-known model, which is 80,000 point neurons and 150 million synapses. And we converted that from NEST to NetPyNE. So that's recently published in Neural Computation, and it's also available for people to use. And an interesting feature is, well, we reproduce the original firing rates and statistics, but we extended it to have an option to downscale the model. So you can select, for example, a 50% size of the model and still maintain the same original dynamics. And we also implemented a new multi-compartment version of the model. So originally it's point neuron, but now we have this multi-compartment implementation where you can start to play around with other features such as recording LFPs, for example. Okay, so let me see what time it is. Okay, so we're quite on track. So I'll now give the control to Joe Graham, who will go over the tutorials, the GUI-based tutorials. And again, here is the link to the GUI so that you can open this link and run the tutorials.
All right. Graham, a neuroscientist and now a Today we are going to go through a few examples using the graphical user interface, the GUI. I guess I should share my screen. One participant can share at a time. Salva, can you stop sharing then so I can?
Sure.
All right, share screen. Yeah, hold desktop, share. So everybody can see my screen, and I've got the GUI up here. So it's www.netpyne.org/GUI, GUI. Can you see it? Hello?
Okay, maybe it's my computer. It's just finally starting. I apologize.
Oh, okay, good. Okay, I'll give it another couple seconds to load here before I start anything. But yeah, in the GUI, tabs along the top here. And this is the workflow you have to follow to build any simulation, to start building up a simulation. First, you have to define some cell types. You'll have to make populations out of those cell types. If you want to connect them, you'll have to add synaptic mechanisms and connectivity rules. And then if you want to use stimulation, you'll have to have sources of stimulation and targets, which that stimulation hits. There's a tab for general simulation configurations, how long does it last, what's your time step, and plot settings. So you can look at what different analyses are available and set some options in there. One thing to notice in the lower left, there's a little arrow that expands the same tabs as on top over here on the left, and you can navigate using either one. One thing to note is that there is a Jupyter notebook built in to the GUI. And so, yeah, if you click on Python on the left there, we get this Jupyter notebook. And I'll just do whos, and we can see we've got Jupyter, Geppetto, NetPyne, Geppetto. These are the things that link NetPyne to the GUI. Yes, and this is synced with the GUI. So any change you make in this Jupyter notebook, in this little Python panel, will be immediately reflected in your simulation, in the model. And any change you make in the simulation of the model will immediately be reflected in the underlying Python. So yeah, anything else we wanted to cover there? That should do it. Navigate the sidebar, Python, and Jupyter Notebook. Yeah, in a Jupyter Notebook, you have to hit Shift and Enter in order to enter anything. Great, so let's start building up our model. We're in the Cell Types tab, and we are going to add a cell type. So we're going to click the plus. It's very easy to build up a simple cell model, but we're just going to load one so it's even quicker, and then I'll show you how we would set it up. So we're going to load this ball and stick HH cell. So it's just a soma with a dendrite and Hodgkin-Huxley mechanisms in there. And we can see we add that. Now we've got cell type 0 here. I'm going to click on that, and we get a new panel over here. Let's call this cell type PYR for pyramidal. Now let's look at what this consists of. So again, we're in the PYR here. Click on that, and then we should be able to click on the section above it. And now we can see this particular cell is a ball and stick. It's got a soma and a dendrite. On the right panel, we can see more information about the soma. So for its geometry, it's a diameter of 12, and the length just changed oddly. Length of 50. It does not have any topology. The soma is typically its own parent section, or the parent section of the neuron, so there's no topology there. And yeah, let me make this a little bit smaller. There we go. Topology. Okay, so yeah, we'll look at the dendrite section. And in the topology, now we can see the dendrite has to have a parent. It has to attach to something. So it's connected to the soma. It's connected at the very end of the soma. Connectivity in neuron is defined 0 to 1. So the 0 is the beginning of a section and 1 is the end of a section, or how long or short. So we'll connect it at the very end of the soma and the very beginning of the dendrite at 0. Great. And then we can look at the mechanisms in each section. So in the dendrite, we just have a passive mechanism. And if we click on that, we can see its parameter values. My internet connection is unstable. Okay, yeah, now it's showing us very slow for me as well. Okay, wow, it's very slow. Sorry, guys. So yeah, it's got a conductance of 0.001 and a reversal potential of -70 millivolts. Let's go back to our soma and take a quick look at the mechanisms in the soma. And here we've got the HH, so the standard Hodgkin-Huxley mechanisms for neuron, and the parameter values for there. So yeah, if you wanted to build up this cell from scratch, you just create a soma, plug in the geometry connected to the dendrite, and so on. But for now, we'll move on to making a population out of that. So we explored, yeah. So up on the top here, I'm going to click on populations. Shrink that so things get a little bigger. Great, so we're going to create a population. And we're just going to call this E for excitatory. It's going to be, yep.
How can you see the units like conductance on those, the mechanism parameters?
Yeah, we use the standard neuron units. So there's no real way to see what these units are from the GUI, but yeah, look at the Neuron website, and the units will be there.
Okay.
Okay. Okay, so we clicked plus on population, and then we named it E. Over here on the cell type drop-down menu, we only have one cell type, that PYR we created. So we'll select PYR. And yeah, there's a variety of ways to specify how many cells you want in your population. You can do the number, you can do a density, you can do grid spacing, so they're perfectly spaced on a grid. We're just going to do a number of cells right now, and we'll do 40. So go ahead and put 40 cells in there. And then, yeah, 40 cells, and then we'll create it and we'll see it. Okay. Yeah, so at this point, we only have some cells and they've been put in space, but we can still create the network and take a look at what's going on so far. Great, so we can see, oh yeah, the soma did get weirdly long somehow. I don't know how that jumps in. We'll fix that in a second. Normally it should look like a sphere. One thing you can do here to make these easier to look at is over here on this little control panel, the bottom button there allows you to randomize the colors. So it makes it easier to distinguish the neurons. But yeah, there's our 40 neurons. The connections plot is not going to be very interesting right now because they haven't been connected. So it's all going to be 0. The 2D net plot, they have been positioned in space. So NetPyNE has a default 100 by 100, I believe, micron space that neurons get placed in. And so they've been placed. No connectivity yet because we haven't set that up, but we'll do that in a moment. So yeah, now on the top right, we're going to click back to edit. First thing we're going to do is fix the pyramidal cells. So we're going to go back to cell types, click on PYR. Click on section, click on soma, and then on geometry. And both the diameter and the length should be 10 microns. Okay, so we've got a population. Now, if we want to connect our neurons, so we're going to have to create a synapse. And yeah, so we're going to create the synapse. We're going to call it EXC 1.1 and 1.0. Okay. So in our synaptic mechanisms tab, we're going to click plus to get a new synapse. And we're going to just call this EXC for excitatory. We're going to use the standard X2 syn. It's a built-in neuron synapse. It's a double exponential. So it's got an exponential rise time and an exponential decay time. And for the time constant, it will have a fast rise time of 0.1 milliseconds. And a slower decay time of 1 millisecond. We want this to be an excitatory synapse, so we want our reversal potential to be, positive, or we'll set it for 0. And yeah, that will create our synapse. Now we have to define our connectivity rules to say how this synapse gets used to connect the different neurons in our populations. So in our connectivity rules tab, we're going to click the plus above connectivity. And yeah, we want to give it a name. Usually we give it descriptive names. This connectivity rule is just going to be from the E population to the E population. So we'll just name it E to E. I believe the weight we want is E to E. Okay, 0.1 probability of connection. Where's the weight? Yeah, 0.005 is what we're going to put in for the weight. And the weight is dependent on the synaptic mechanism. It'll vary with different mechanisms. For the probability of connection, I think we're just going to put in 0.1. So it'll be a 10% probability of connection. So between any two cells, there'll be a 10% chance that they end up connected. The other ways you can define connectivity are with convergence or divergence. So convergence is from how many neurons does one individual neuron receive inputs? And divergence is how many postsynaptic neurons does one neuron touch? So you can do it by probability, you can do it by convergence or divergence. And yeah, you can even set up probability based on distance between cells or position within the network, but that's more complicated. We won't get into that yet. For the connection delay, I think we're just going to do 5 milliseconds. Yeah. So when the axon spikes, it'll wait 5 milliseconds before it gives the postsynaptic, in this case, excitatory postsynaptic potential. And yeah, you can also set connection delay based on distance. So it's very common. Most of our models use the 3D distance between any two neurons to define the delay between them. Okay, so we got the general connectivity set up. Now we need to set up the presynaptic cells and the postsynaptic cells. So we'll click on the presynaptic cells here. And yeah, it's just we're gonna pull from the E population. Like we said, this is from E to E. You could also define connectivity by cell type, only connect to different cell types, range of locations. There's lots of different ways you can connect your model. We're gonna go E. And then we're going to click on postsynaptic cell conditions. And same thing, we're just going to feed it into population E. Great. So now we have synapse and connectivity. So we can create the network again. And now we should see that connectivity. So, oh, I need to actually, okay, there we go. It's simulated it. So now we can see that, yeah, you've got all the cells in their 3D positions, and now you can also see the connectivity between them. All the plots that come up are interactive. So if you hover over the plot, you can get more information about these individual points. I'm going to zoom out a little bit here so we can see the rest. Yeah, you can save any plots you want. And there's ways you zoom in and out, and a variety of ways to interact with these plots. Now our connectivity plot, yes, we can see it's no longer 0. Now we're looking at 8.1 times 10 to the negative second as the strength between these cells. Yeah, the standard way to look at the connectivity is population to population, but we can also compare it, use a cell to cell, so we can see the individual connectivity in those cells. Great. So let's go back to edit now. This network isn't going to do anything right now without any stimulation to kick it into gear. So we're going to add a source of stimulation, and then we're going to connect it into just one of our cells. So let's click on the Stim Sources tab at the top there. And let's see here, what are the settings going to be? Yeah, so we're going to use a current clamp. We'll name it iClamp1, delay of 20, duration of 5, amplitude of 0.1. Okay, so let's click the plus above source. And it's Stim Source 0 default name, but we'll call it eye clamp 0 since it's an eye clamp. Yeah, instead of a net stim, clamp. I think it was going to be 20 milliseconds, duration of 5 milliseconds. 5 milliseconds, and the amplitude 0.1. So 0.1. Oh yeah, so here you can see it says nanoamps in parentheses, milliseconds in parentheses. So we do have the units in some places here. Great, so we've set up a current clamp. Is there a question or? Okay. We've got a current clamp simulation set up. Target does not go into anything right now. And yeah, my internet connection is a bit stable. I apologize for that. Stim targets. I can't see with that message there. Go away. World. Okay, well, what if I go over here? Stim targets, stim sources, stim targets. It's really strange. I can't see. Give me 1 sec. What if I minimize this? We'll come back up clean. All right, sorry guys, technical difficulties. NetPyNE.org/GUI. Give me 1 sec to get this loaded again. It should have saved all my stuff, I hope. Otherwise, we'll quickly just load the tutorial. Yeah, so once we get the stimulation target, source and target connected, then we can fire up the simulation. That current clamp will, after a delay, the simulation will start 20 milliseconds later. That current clamp will kick in for a duration of 5 milliseconds. And we'll feed that into one cell. And that will kick our nuke into action. Let's take a look. I have a lot of NetPyNE right now. It spools up, so more and more users, Google automatically starts adding more cores available to people to use, but that can take a while.
Joe, maybe if that one crashed for you, you can try opening like an incognito browser, and that will open like a new.
Yeah.
We should have over 60 nodes on Google Cloud for this, so there should be more than enough, I think.
Okay, good. Good, okay, here we go. It's slowly coming along here. Did you have the GUI up and running, Salvador? I don't know what else to do here.
I'm loading right now, so I can.
Okay, yeah, if you get it loaded, maybe I can talk and you can share your screen.
Sure.
Yeah, it does not want to load for me.
Yeah, it's working for me now.
Okay, yeah, let me stop sharing Salvador, and I'll tell you what to do, and you can do the screen. Let's see here. Where do I have stop share? Okay, yeah, if you could share your screen, Salvador.
You see it now?
Well, yet. There we go. Now I see it. Okay. Yeah. So everybody sees solve the screen. Yeah. At this point, I think we'll probably just load tutorial 1 from the menu, just so we don't have to re-enter all that stuff. Click on tutorials, tut 1, and it'll load up those cells. And we got the connectivity rules done. The stim source. Let's look at real quick. And yeah. So there we go. So yeah, it's the current clamp we set up with a delay of 20 milliseconds, lasts for 5 milliseconds. Now we'll want to click on the stim target and set the cell we want it to go into. In this case, we want to give it a descriptive name. So we're just going to feed it into cell 0. A good name is iClamp1 to cell 0. In the stimulation source, we only have 1, so that'll be the only one in that drop-down menu below. We have to say which section in the postsynaptic cell do we want it to hit. We want it to hit the dend. We've got a soma and a dend, and we want it to connect to the dend. For the location, we'll just do it at the very end of the dendrite. So again, 0 would be the very beginning of the dendrite, 1 is the very end. We'll have this feed into the very end. And yeah, so now we'll want to look at the conditions there, yeah? Oh no, that was the conditions, right? No, yeah, we got to set, yeah. So we don't want to target population. We just want to target a single cell. So the very bottom option on that list, yeah, you would type a 0 in that box and then click the plus. That's already been done. We can see that cell 0 is targeted by this. Great. So that's our stimulation sources. Populations, cell types. Hold on one sec. I got lost in the presentation here. Okay, so for the configuration, yeah, let's go to the configuration now. We set the duration to 200 milliseconds. I think the default is 1,000, 1 second. We'll just do a short simulation here. Time step 0.1 is enough for this simple simulation. The one thing we're going to want to do in the configuration is set up what we want to record. So we're in the general tab right now. We're going to click on the record at the top there and set up what cells we want to record from. Cell 0 is the one we're feeding the current clamp into, so we might as well record there. And we have to specify what we want to record. You know, there's a lot of stuff inside each cell. In this case, we just want to record the voltage at the soma and the voltage at the dendrite. And so, yeah, this is sort of like pseudo code to put this in there. I can name it the underscore soma. For the soma voltage is a good descriptive name, but then you have to specify the section, the location, and which variable, which neuron variable you want to record there. So yeah, we'll record the soma in the middle, 0.5, and the variable record is V, the voltage from neuron. And the dendrite, same thing, except we'll record at the very end, a location of 1, and our variable will be V. Great, so that will set up our recording. Now let's look at the plot settings, and we can make a few adjustments to our analyses. So yeah, for this one, we have 2 modifications to the plots. One is the traces. Cells to include, we're going to include the 1 cell that we set to record. And yeah, 1 fig per cell per trace. Overlay data. Yeah, if you want to, yeah, so normally it'll just plot traces separately unless you click to overlay them, in which case they're nicely on the same plot. You can see them better. Yeah, let's look at the iPlot raster options, Salvador. There we go. And yeah, we'll include all the cells for the entire time the simulation runs. The one thing we might want to do, no, there's only one population. There's no need to invert the axis on this. The one other plot I wanted to change was to show you that you can also plot the connectivity between cells. So Salva, if you would add a connectivity plot there. So he's going to click the plus, go down to network connectivity plot. And group by is normally by population. We're going to put it by cell instead, so we can see the connection between individual cells. The feature to show, we're going to want it to be weight. Strength is the default for between populations, but between cells, between any two individual cells, you just have a single weight. And so we want to do the weight, and that'll be great. Great. So yeah, we've got everything in our simulation set up. So now we can click on Create Network. And then that will instantiate it. Shouldn't take too long. It's a pretty simple network. Great. We can see our 40 cells. Now the soma is correct, 12 by 12 instead of the 12 by 50 it got bumped up to for some reason. And yeah, so let's go ahead and rocket ship it. We'll launch the simulation and look at the output. Great. So yeah, the first plot that comes up is that connection weight matrix. Before it was just a single square, right? Because it was just one population to one population. There's only one value. Now we're seeing the cell-to-cell connectivity. And the weight, we just have a standard weight between them all. So it's all exactly the same weight. But you can see that there's about a 10% chance of the two cells being connected there. So yes, let's look at the other plots. We can look at the 2D network plot. Yep. And yes, so that's our neurons situated in 3D or a 2D view of it, and you can see the connectivity between them. Great. Let's look at our traces. Give it a second to come up here. Okay, the raster plot came up. Okay, well, on the raster plot, you can see that cell 0 is at the very bottom. And about 20 milliseconds in, we put in the current clamp, and that causes that first spike in cell 0 that gets transmitted to the cells it's connected to, and then that for some activity. Yeah, we could put some plot underneath this. We could do the.
Sorry, Joe, the cell traces, I think I messed up something before when I was clicking around and I removed the recording of the cell 0. So that's why they're not showing here. I can go back now and add it. You want to show the spike histogram?
Yeah, and we can line that up below the raster plot. That's kind of fun. You show them how you can move the figures around and rearrange them. So you can drag these figures to make them whatever size and shape you want in the screen there. So it's useful to, and we used to have them scale automatically. That's a problem we'll have to look into. But this way, yeah, with the raster plot right above the spike histogram, you can see how when there's more spikes, your average cell firing rate is higher. You can arrange these in all the different ways. Yeah, and that's about all we really want to see on this first simple tutorial. Salvador, anything else you wanted to talk about on this one? If you want to get the traces going, we could try that. Yeah. Good. Okay. All right, yeah, try that again. Cell 0 is being recorded.
Not sure why, but yeah, not sure enough.
Yeah, anyway, normally the traces should show up and we would talk about them. You'd see the dendrite spikes first when that I clamp, when that current clamp comes in, and that drags up the soma voltage until it starts spiking. You guys can load tutorial 1 on your own in the GUI and run it, and you'll be able to see all those analyses. Yeah, so for now, yeah, let's move on to tutorial 2. This is to, yeah, so under File, let's go to New, and that'll create clears the kernel, ready to start from scratch. On this tutorial, we're going to show you that you can also use morphologically detailed cells in your simulations. And we're going to actually import it to kind of show you how you can import outside cells into here. So yeah, instead of let's create a new cell type. And yeah, import cell template from file at the bottom of that menu. And yeah, so we're going to have 2 pyramidal cells and 2 interneurons. So let's call this one PYR or PT, something to specify it. And then, yeah, we're going to want to load it. And so you click on the file explorer there. And in the cells directory, that's where we've got a few cells that you can load and play with. If you upload a cell, if you upload a Python or a Hope cell to the GUI, then that'll show up under uploads. And so yeah, you can get your own cells uploaded to the GUI and then add them using this method here. But yeah, let's select that PT cell.hoke. Yeah, the path to the mod directory. So these neurons have a bunch of mechanisms which require mod files from Neuron to use. You have to link to where those mod files are, and that should be good. We should be ready to import. And we've got our PYR cell. So let's take a look at the cell sections. Great. So we can see that this cell has a ton of sections. So it's got 1 soma, 1 axon, and then a whole bunch of basal dendrites, just called dend, and then a whole bunch of apical dendrites, the sort of tree growing upwards. And each one of these is going to have its own geometry, so its length, its diameter, its own topology, so who to connect to, and it'll have its own mechanisms as well. So if we want to, I just click on the mechanisms real quick to see what's in the dendrites, Salva. Wow, 1, 2, 3, 4, 5. We got 10 different mechanisms in the dendrite here. Some calcium currents, an IH current, potassium currents, sodium, obviously passive. So yeah, this is obviously a much more complex model than the last one we ran. Great, so we got our pyramidal cells. Let's add a couple interneuron cells, which we will also import. So we're going to go to cell types, click plus above cell to add a new one. And we'll import the cell template from file. And we'll call this one INT or something to indicate that it's an interneuron. Yep. Go to cells. And this one is the, the SRI.hoke. Select that one. So yeah, when you have a cell model that you want to import, in the cell model, there'll be a way to instantiate it. That's what this template slash class name is. So whatever name is internal to instantiate the model. I don't recall what it is offhand on this one, Salvador.
Okay, I don't recall either, but I'm gonna try just SRI.
Yeah, perfect. Hopefully that's it. And we'll import that. Okay, so we've got 2 cell types. Let's see, did the in-cell work? Uh-oh. Yeah, it looks like that did not.
Yeah, it worked. Yeah.
Oh, did okay.
Yeah, we have the pyramidal interneuron, and inside we have the
Perfect.
sections.
Okay, so now we've got these 2 cell types. Now we want to create populations out of them. So we'll go to our populations tab. And we'll add a population. And yeah, for the pyramidal cells, we can call it E, we can call it PYRs, we can call it whatever we want. The cell type will be the PYR that we imported. In this case, we can do 1 or 2. It's very detailed. So the normal tutorial has two of each. We can do that. And then we'll create another population for the interneurons. We'll just call it I for inhibitory. It's going to be made up of the interneurons we imported. And we'll just create 2 of those as well. And so let's go ahead and create that network, Salvador, and they can see the morphologies in space. And I've got about a half hour left, right?
Yeah, 20 minutes actually, because we have a break.
20 minutes. Yeah. Perfect. That should work pretty good. We'll go through tutorial 3 sort of quickly. And again, this is a very complex, 2 very complex morphologies, and each one has a bunch of mechanisms, a bunch of different currents flowing. We're gonna play with the color a little bit, Salvador. Oh, let's change it to the black background, which I like better. So yeah, you can change the cells' colors so that they're easier to see. And the NetPyNE, if you go to color preference, I think it's easier to see most of these on a black background. So I actually prefer that one. Yeah, that's obviously much easier to see. Let's make the interneurons a little more visible. Yeah. Great. Zoom in, we can see a couple of small interneurons around these 2 very large pyramidal neurons. Perfect. We could, input a stimulation or something and connect these cells to see what happens. But really, we just wanted to show you that you could import and that you could get morphologically detailed cells into the GUI to explore and play with them, see them. So at this point, we're going to move on to tutorial 3, which is a little more complicated, and we're going to involve more analyses. So now we're going to add some reaction diffusion, and we're going to put in, we're going to measure local field potentials. So we're going to model an electrode, put into the model space and recording. So again, let's go to File, New, just to clear the kernel, reset everything. And then to load tutorial 3A, which is low IP3. So it takes a while to load, so we'll go ahead and start. And then can you pull up the slides with the IP3 figure, Salvador? There we go, tutorial 3. Oh, yes, and in this case, we have a strange bug in tutorial 3. So if you create and analyze separately, it breaks. So if you go into model, I believe, click on model, Salva, and then view options, and then click on automatic simulation instead of manual simulation. Otherwise, this weird bug causes a crash. We'll get that fixed as soon as we can. But so model, explore view options, automatic simulation. And then, great, we can click create and simulate network. And that is going to take a while to do because I think there's 60 cells in this and connectivity. It's pretty complex. So while that loads, we're going to talk about what this model is doing. So we go to the next slide there. Great. So so we're going to explore reaction diffusion and LFP in this case now. And what we're doing is we're not actually modeling the glutamate receptor, but this M-glutamate receptor, when activated, causes an increase in IP3 in the cytosol, inside the cell. This increase in IP3 in the cytosol causes in the endoplasmic reticulum, there's IP3 receptor channels. IP3 comes in, hits that, opens those up, and then calcium flows from the endoplasmic reticulum into the cytosol, where it can affect cell voltage and all that, and interacts with calcium-sensitive potassium channels, and it activates those. Then you get potassium flowing into the cell, which obviously is a hyperpolarizing current, and that is going to end up reducing the cell firing. So this is a multi-scale network where we're looking at a very small, in the RxD setup of this, we created a cytosol region, endoplasmic reticulum region, and an extracellular space. And we're actually modeling the reaction diffusion of IP3 and how that affects calcium, and how that, and then that's going to go on downstream calcium sensitive potassium currents. So yeah, this scales from the very, very tiny subcellular reaction diffusion stuff all the way up to, we'll put in LFP electrodes. So we'll be able to measure local field potential on this model as well. So from the very, very small scale up to circuit level scale. Let's take a look at the loading, and it's still going.
If you want to mention something about the structure of the network?
Yes. So this, the connectivity on this one is set up based on the layers. And so, and distance. Yeah, I'd have to. Yeah, do you want to talk about this, Salvador? Without seeing it in front of me, I can't remember exactly what it is.
No, yeah, I'll briefly mention so it's supposed to model like a very simple cortical network. So we have 3 layers, layer 2, layer 4, and layer 5, I believe. And each one has 2 populations, an excitatory and inhibitory population. So it's very simplistic, but you see sort of the laminar structure. And then, yeah, we have 2 connectivity rules that we can show you now within the connectivity rules here. So you see how they're expressed mathematically, but they're like a very simple mathematical expression that results in complicated connectivity. So that illustrates some of the power of NetPyNE.
All right, here we go. So we can see our pyramidal neurons there. Nicely arranged in the layer structure. Yeah, maybe if we color them by layers, Salva.
Yeah.
Perfect. Yeah, so we use 2 connectivity rules in this, excitatory to all and inhibitory to excitatory. But yeah, with some very simple distance-based rules, you can get some very interesting connectivity out. Right. So yeah, now we've got different colors in the different layers. You can see that it's set up as sort of a simple cortical model. And yeah, let's look at the connectivity then, huh? Great. So like Salvador was saying, layer 2, layer 2, 3, layer 4, and layer 5, excitatory and inhibitory in each. And yeah, so this is the resulting connectivity. In order to see the rules, we'll have to go back to edit, but let's look at the other plots here first. The 2D net. And that's a little hard to see with a black background, maybe. They're just very small. Yeah, so we got the cell traces. We set it up to record the internal calcium concentration in the soma. So that's the next plot. We can see that the calcium increases. I believe the next one, yeah, the extra calcium outside the soma, which decreases. And the final trace we're recording there is the potassium current, which is affected by the calcium concentrations. Yeah, do you want to go back to edit, Salvador, and we can talk about how we set up that connectivity? So you can see we got two rules: excitatory to all. So excitatory feeds into itself and into the inhibitory population. And yeah, so the probability of connection is for E to all, it's just 0.1. And yeah, the weight is what's interesting here. The strength of this connectivity is based on the Y position. So the vertical position within the cortical column. And the connectivity delay now, because we're having distance be important, it's now the distance between any two cells divided by our propagation velocity. So now our connectivity takes longer to activate a cell that's further away. Yeah, so for the I to E, and this is a more complicated connectivity pattern here. So now for the probability of connection, it's just not a probability. Now it's on the distance between. So we know that interneurons, inhibitory interneurons, are local, right? They mostly affect the cells that are nearby. And so, yeah, we want the probability of connection to be higher when it's very close, and to drop off as cells get further and further away. And yeah, so I think yeah, and so then what we're going to do now is we're going to increase the IP3 concentration and run this simulation again. And that IP3 increased concentration will, at the very local subcellular level, will affect network spiking and the spiking of cells.
Yeah, I just went back to run the model so we can see the original results without the low IP3.
Yeah, good idea.
Because we didn't see the LFP and all that, so unfortunately it has to run it again.
Yeah, I guess we should have looked at all those first before we redid it. Live and learn.
Yeah.
So there's a couple of questions in the chat, by the way.
Oh, perfect. Okay, let's see here. If I want to run the model for a range of parameter values, for example, within a for loop, how would it be possible in NetPyNE? Can we export the, okay, first of all, yes. So we have batch simulations to allow you to decide as many parameters as you want. Mostly I do 2D exploration. So choose two parameters, set up a few values for each one of those. And then our batch simulation will go in, put in those parameter values, run the entire simulation, save the output and the figures. And so, yeah, you'll want to look into running batch simulations in NetPyNE in order to loop through values. And then the next question was, can we export the code of the established model to Jupyter or Spider and run the model /NetPyNE there? Yes. So in the GUI, I believe if you click on File, you should then be able to click on Export to Python, I believe it is. And that'll allow you to save the Python file of your complete simulation, and you can run it on your own machine. You can, yeah, you can do anything with it at that point. So yes, excellent questions. Thank you for asking.
I'll paste in a bit the Jupyter Notebook tutorial for running batches, which we developed during the course. We did like a 2-week course on Neuron and NetPyNE recently. So we have a bunch of tutorials, and we also have a YouTube channel with all the video lectures. So we'll post the link to those in a bit in the chat, but they're also on the slides.
Yeah, yeah, and yeah, like Salvador was saying, we had a complete course running through NetPyNE and Neuron. It was a full week of courses, and each one of those is available online on our YouTube channel. So yeah, if you want more information about anything, you can get a lot of videos there to see exactly how we do a lot of stuff. And yeah.
Should be, let me just paste the link to that tutorial quickly.
Perfect. Yeah, good idea.
So here's the link to all the tutorials. And the one you're interested is in this one, the NetPyNE batch. There's also more information on the website as well. Okay, so it's finished.
Oh, good. Okay. So yeah, now we'll look at the other analyses. Nice. All right, so now we can see our local field potentials. So in our model specification, we said where our electrodes are going to be in space. And this is the local field potentials, the sum result of all the activity going on. Great. And you can see the top is the average of all the LFP electrodes. And then there's 3 electrodes. And then the top trace is actually the average of those 3. And this is the power spectral density of the local field potentials. So that's at any given frequency, how much power is there? How much of this activity is at that frequency? And we can see that, yeah, we're at about 25 or 30 hertz here largely. And now we can see our RxD, our reaction diffusion. This is the calcium concentration. And we're looking at the entire network, we're like the cortical column, basically. And yes, so whenever the cells are activated, you're going to, you're going to decrease the local calcium concentration because it's being moved around.
Yes, this is the extracellular calcium concentration. So when the cell is firing, the calcium channels open and you get the calcium flowing into the cell, so the extracellular decreases, and that's what you're seeing here. Cool. So
yeah, and then so now we can increase the IP3 concentration, and we'll see how that has effects all through the network, through the behavior. And so there's a line where have you paste into the, and I'll put it into the chat as well. We're going to modify it using this line of code in the Python terminal, which I just pasted into the chat. So yeah, NetPyNE Geppetto is the link to the GUI. And in our net parameters, which we set up in the reaction diffusion parameters, our IP3 species, the initial concentration we want to set to 0.1. So Salvador, before you hit enter on that, actually, why don't you delete equals 0.1 so we can see what it is beforehand? Just delete the final equals 0.1. Oops.
It was just showing like the different components inside.
Oh, great. Yeah. Yeah, so in the network parameters, all of the information is in this dictionary structure in there. And we can see that right now our IP3 initial concentration is 0. We're going to increase that so that we can then explore the simulation and see the results of that. So now we'll set it equal to 0.1, shift enter. And great, so now we want to run that simulation again. And then we can look at the analyses and we'll discuss the differences. Yeah, this will probably take a little while to load again.
So maybe Joe, you want to
so after this, Salvador is going to walk you through more. Yeah, what's this?
Yeah, you can explain how to maybe load this Google Colab so that we're gonna do after the break.
Oh, great. Okay, yeah, let me copy that link into into the chat as well. Where are we here?
So after the 10-minute break for the coding tutorial, we're going to use Google Colab, which allows you to run these Python scripts interactively online. And so you can actually make a copy of an existing Google Colab or Jupyter Notebook. And so here's the link. If you paste this link, you should get the original one. And then you can make a copy so that you can edit it yourself and modify it.
Yeah, go to File, Save As, so that, yeah, you get it locally, and otherwise you can't change it. Yeah, save a copy in Drive is what you're going to want to click on. Yeah, so the GUI is very useful. You can switch back and forth between programmatic and the GUI. You know, as we said, you can go File, Export to Python. You'll get a Python script of your thing. You can do it programmatically, mess around with stuff, and then you can always get it back into the GUI by using the Python, the Jupyter terminal there. You can paste in your entire model, run it, and it'll be active in the GUI for you to explore visually.
Yeah, and I'm not sure if we showed the Jupyter Notebook interacting with the GUI, but yeah, they're synchronized both ways. So you can basically change anything in the Jupyter Notebook and it will be reflected in the GUI and the other way around. So they're like in sync.
All right, our simulation ran. Okay, and now we can see the spiking is different. The spiking is less than it was before. And yeah, the internal, the calcium concentration in the soma, obviously, is different now.
Yeah, so this increased because we increased the IP3. So the IP3 binded to the ER, and that released more intracellular calcium. And that is what's affecting. Yeah.
And yeah, it affects the potassium currents, calcium-sensitive potassium currents.
So yeah, so we got much more calcium potassium currents, which decrease the firing rate here, and also in the LFPs.
Yeah, you can see it trail off towards the end now.
Yeah. So by changing this sort of RxD molecular level parameter, the IP3, it had a sort of chain reaction and changed the biophysics of the cell and the firing rate of each individual cell, and then eventually the network dynamics, reducing the LFP. So we see directly the relationship between molecular reaction diffusion and the more large-scale measure LFP signal.
Yeah, so a great multi-scale example from molecules all the way up to LFP.
Okay, so thanks everyone. We'll be back in 10 minutes after the coffee break with a coding tutorial looking at oscillations in networks.
All right, thank you all very much and see you in a bit.
Okay, so we're gonna start the last hour of the tutorial. And now we're gonna do a programmatic or coding tutorial looking at NetPyNE and a very simple network which shows some oscillations. So to start with that, we're gonna use a Google Colab, which allows you to run this code interactively online. So we all have the same setup and it's easy to follow. So if you click on this link, it should take you to the Google Colab, which is right here. And then once you're here, in order to be able to edit and use it yourself, you have to make a copy of it. So for that, I believe you need to be logged into your Gmail account. And you need to click on File, Save a Copy in Drive. So I'm gonna give you a few minutes to do that. Here's in the slide, it shows you what to do. Please, if you have any questions, let us know. If you're having any issues copying this Google Colab. Just check the chat. Okay, so I'll just wait a couple minutes and then I'll start on the tutorial. Okay, so hopefully you all have your Google Colab ready for use. So the first thing that you see here in the first cell is a couple of instructions just to set up the modules we need. So we need Neuron and we need NetPyNE, the different Python packages, and Matplotlib. And we're gonna import the two main modules from NetPyNE. One is specs, and it's required to define the specifications, the model specifications of the model. And the other one is sim, and that is required to actually create the network, run the simulations, and analyze the results. So to run the cell in Jupyter Notebook, what you have to do is press Shift Enter, or you can do click on this play button here. I'm just gonna go ahead and click Shift Enter. So now it will install all these packages locally in this Google Colab. Okay, so I think that is done. I think this command prevents it from showing all the output, but it should be ready. And now we're gonna have a look at this code here. So this is a very basic model written in the NetPyNE language. We're gonna see the different components. As you will see, it's very similar to what we saw on the GUI. So the components are very similar. The first thing we have to do is create this object called NetParams inside the specs package. And this is essentially the object that is going to contain the whole model specification in NetPyNE. So NetParams is an object which has different substructures, different attributes inside it. And the first of which we're going to fill in is this NetParams cell params. And this corresponds to the GUI. If you remember, the first panel we had was the cell parameters. So this is equivalent here. And The structure of the cell params object is essentially a dictionary as well. So in the name of the dictionary, we can provide the name of the cell type, in this case pyramidal, and inside we're gonna fill it in with a dictionary that contains the different sections. So there are many ways to fill in a dictionary in NetPyNE. Here we're just showing an example. So first we're creating an empty dictionary and we are adding a section called Soma. The Soma, this is a predefined structure standardized in NetPyNE. So we always need to have this geometry, geom, and the mechanisms, which are also gonna be dictionaries. And we start filling in the information. So for geometry, we're gonna set the diameter and the length of the neuron to 18.8 micrometers. So those are sort of a cylindrical or spherical neuron, and the axial resistance. We're then gonna add inside the mechanisms, we're gonna add the standard Hodgkin and Huxley mechanism, HH, and we can set the parameters of HH inside this dictionary. So the conductance of the sodium channel, the maximum conductance of the potassium channel, the leak channel, maximum conductance of the leak channel, and the reversal potential of the leak channel. And finally, we just add all this information of the sections inside this netparams.cellparams structure, which contains the different cell types that we're going to define in NetPyNE. In this case, the pyramidal neuron. The next step is to create populations, as we saw also in the GUI. So in this case, what we're going to fill in is this netparams.popparams structure, and we're going to add two populations, an excitatory and an inhibitory, E and I. Note that the labels of these populations are the keys of the dictionary, and they can be any arbitrary label. And very simply, for each of the populations, we just specify the cell type, in this case pyramidal, which is the only cell type that we have defined so far, and the number of cells, in this case 20 cells. Notice that even though we have two excitatory and inhibitory population, we're going to use the same cell type, a pyramidal cell, just for simplicity, as we want to make this example very straightforward. But in theory, you would define a different cell type here, some inhibitory cell type, and then use it for this population. Okay, so this is going to give us 40 neurons, 40 pyramidal neurons in two populations. The next step is we define the synaptic mechanisms or synapses, synaptic types, in this structure called netparams.synmecparams. And we're going to define two different ones, an excitatory and an inhibitory synapse. Inside the dictionary to define these synapses, we have to specify the mod file used for the synapse, in this case, the double exponential, x to syn, and the parameters of this synapse. So this is the rise time, the fall time, tau1, tau2, and the reversal potential. Okay. Notice that for the inhibitory cell type, we use a reversal potential of -70 to indicate that it's inhibitory. Okay, the next step would be defining the stimulation of the network. And the way this is implemented in NetPyNE and in other similar standard languages like NeurML is using the source of stimulation first. So we create a new source of stimulation. In this case, we're going to call it background, BKG. And we're going to specify it's of type NetStim. Remember, NetStim is a built-in spike generator in Neuron. So it's a mod file that basically generates spikes at a given rate, firing rate, or interval, which is the inverse of the rate. So in this case, we want to specify that the firing rate of this spike generator is going to be 50 Hertz, and we want to have a noise of 0.5. This relates to the randomness of these spike times. And the next step is to say that we want to connect this background input noise, this NetStim, to some of the cells in the network. And here we can use these sort of conditional rules in NetPyNE to say that the source of the stimulation is going to be the background, and the conditions of the cells where we want to connect this source is going to be all those in the population E. We're basically just going to provide background stimulation, these random spiking inputs to the excitatory population. We're going to do this with a weight of 0.01. So all these are going to have be connected through synapses. So we have a spike generator that's going to connect to cells in the E population via synapses, and the synapses are going to have a strength of 0.01. A delay of 5 milliseconds, and they're going to be connected using the synaptic mechanism excitatory. Okay. So now we have a population of 40 cells. We have the different types of synapses, and we have background stimulation into a subset of the cells, the excitatory cells. So the next step we're going to do, and that will be the final step for building the network, is define the connectivity. So in this case, we're just going to have two connectivity rules. And we're going to connect the excitatory cells to the inhibitory cells and the inhibitory cells to the excitatory cells. So sort of creating a feedback loop. So we can see that for each of these connectivity rules, we have a number of parameters. First, we define the conditions of the presynaptic cells that we want to connect. In this case, again, it's a very simple condition. It's all the cells in the population E. But I want to note here that we can use more complex conditions. So for example, we could say all cells that have the cell type pyramidal, for example. Or if we had different cell types, it could be like a PV, parvalbumin cell, and so on. We could also specify things like the location of the cells. So for example, the Y location, which is the depth, we could say all cells between 200 and 400 micrometers. And these conditions are additive. So we would need to match both cells being in the population excitatory, as well as being with a cortical depth Y location of 200 to 400 micrometers. Okay, so the next step, as you see, is defining the conditions of the postsynaptic cells. And in this case, we're going to say the inhibitory population. Another parameter that we define here is the divergence. And notice that there are several ways to define connectivity. As I said before, we can define using probability of connection. So this is a value between 0 and 1. Divergence refers to the number of postsynaptic cells that are targeted by each presynaptic cell. And we also have another property that we can use, which is convergence, which is the number of postsynaptic cells targeted by, the number of presynaptic cells that project to each postsynaptic cell. Okay, so in this case, we have divergence of 1. We set the weight, delay, and we specify that we want to use the excitatory mechanism, synapse. Okay, so moving on to the other connectivity rule, we have, in this case, we're connecting the cells from the inhibitory population to the excitatory population with a probability of connection of 0.7, a specific weight, and some delay. I think this initially should be 5 milliseconds. So this is one of the parameters we're going to play with afterwards, just to show changes in the oscillations. Okay, so we have finished setting this netparams object, where you define the parameters of the network. And now we're going to move on to defining the simulation options or simulation configuration. For this, we have to create a separate object called simconfig, where we specify properties that are specific to these simulations. For example, things like the duration, we want to run for 1 second, the integration step, 0.025, whether we want to have verbose output or not, the traces that we want to record. So in this case, this is another dictionary where we specify the keys, the voltage of the soma. It's an arbitrary label. And then we specify what we want to record. So we want to record from the soma at location 0.5, the variable B, the voltage. Things like the recording step, we want to save to different formats. You could save to pickle or to JSON, for example. And finally, the things that we want to plot. So you can define here beforehand, after running the simulation, you want to plot a number of figures. And in this case, we just want to plot the traces. So for one of the cells, we just want to show one of the output traces. We want to plot the raster plot. This order inverse just refers to the way the populations are shown. And order inverse is usually more intuitive because it matches the legend. Sync lines, I will explain a bit when we see the plot. And we also have plotting the spike histogram, which is a nice way to see the oscillations. We have that for the excitatory and for the inhibitory populations. And finally, the rate spectrogram. So this is the spectrogram of the firing rate of the cells, the spike times. And so it's a nice way to illustrate also the oscillation frequency of the network. Okay, so now we can go ahead and run this cell. Press Shift Enter, or you can click on the play button here at the left. Okay, and so we can see that we get some output. So initially, NetPyNE, oh, just to mention, I forgot the only command that we're actually running is this one here at the end, which is sim.create simulate analyze. And we pass these two structures, the net params and the sim config. And so NetPyNE takes all these parameters that we have defined, which was just basically filling in dictionaries, and will create a network. So all the neuron objects required to run the simulation will then run the simulation in parallel and will plot or do any analysis that you have specified here at the end, all together with a single command. And this is the output that you get. So we see NetPyNE creates a network of two cell populations. Right now it's running on a single host, but you could run on multiple nodes, multiple cores. It creates 40 cells in total, makes 299 connections based on the connectivity rules we specified. It adds some stimulation, some steams, in this case, these net steams that provide background input to one of the populations, the excitatory one, and then runs the simulation for 1 second. We then provide some analysis. The output spikes, it generates 580 spikes. And we can see the plots that we asked for. So here, the first one is the voltage trace of one of the population of one of the cells in the excitatory population. We also see this raster plot. And as you can see, there are these red lines coming down. So this is the option that we set here, sync lines, and I'm just gonna set it to false so that you see the difference. Okay, so if you set those lines to false, you just see a normal raster plot where each of the dots represents the spike time of one of the cells. And the useful thing about these red lines is they're essentially a single vertical line for each spike time. And it gives a very intuitive idea of sort of the synchrony of the network. So if all the red lines are close together in different bands, different steps, then that shows that the network is quite synchronous. And if you end up seeing the whole plot has lots of red lines all across the plot, then there isn't much synchrony. So in this case, you see there's relatively high synchrony. So you can see clearly differentiated bands of red lines. You also get a synchrony measure here at the top of the raster plot that says 0.75. That is a measure between 0 and 1, how much synchrony there is. And you can see a similar intuitive representation of the oscillations in the network here in the spike histogram, where you see the peaks of both the excitatory and inhibitory cells. Okay, so The idea here, as you can see, is that we provide some background input to the excitatory population that fires first here, and that is connected to the inhibitory population, the yellow line, so that fires right after it. And then the inhibitory population is connected back to the excitatory one. So it provides some inhibition, which is this lack of activity here. And then when that inhibition dies off, you get again another excitatory peak. And that results in the oscillation. So you have a feedback between the excitatory and inhibitory cells. And the firing rate spectrogram shows a nice representation here of the firing of the network oscillation frequency. We see that it's about 20, this would be 30, 25, so around 22, 23 hertz, more or less. It's a strong power frequency here that lasts the whole simulation duration. And you can see, so if you counted these red lines, they're also around 22, 23 hertz. Okay, so that matches the spectrogram that we're seeing. Okay, so what we're gonna do now is try to modify this network in here interactively and run again and see changes in these oscillations. So just to check any questions, any issues? I think there's a question here. Can we plot LFPs? So that's a good question. So since we have a very simple network, the LFPs are not going to be very realistic. So we have not point neurons, but they have single compartment neurons, just a soma here. So since the LFPs are calculated from the recording the currents of all the different sections of the cell, they're essentially not going to be very realistic, but you could try to plot them. So actually, I can try to do that quickly here. So in order to plot the LFP, we just need to specify here record LFP, and we specify the location of where we want to plot the electrode, we want to place the electrode. In this case, we can just say 50, 50, 50. And this is by default, the size of the network is going to be 100 by 100 by 100. So if we put it right in the center, we're most likely to get some activity. And then we would want to plot this LFP. So that would be plot LFP. We can just set that to true, and it will use the default options. So I think now if we run this, we should get some attempt at LFP signals, but it's probably not going to be very useful because of the simplicity of the cells we're using. It takes a bit longer because it needs to record all the LFP signals. And okay, get an error here. Let me just include the main. So the LFP signal has several plots you can include, and I'm just gonna show the main one, which is the signal and the spectrogram. Let me just check the syntax for that. So we can actually, it's a good chance to show the documentation. So if you go to netpyne.org, you can just type here plot LFP. And that takes you to the package reference for plot LFP, where you can see all the different options of this function. And if you see one of them here says plots. So within this function, you get a number of plots. You get the time series of the LFP signal, you get the power spectral density, you get a spectrogram, and you get also the locations of the electrodes. So I think for some reason, the locations are giving an error because it needs to plot a 3D plot and it's not working in the Jupyter notebook. So I'm just gonna say I wanna keep the 3 other plots here. So plots and series. So I'm gonna try running this now. Okay. So it's now running the simulation. Okay, so now we got an LFP signal. And it actually doesn't look too bad. Let's see. So this is the sort of raw LFP signal that we got. Yeah, so it's interesting. We have, it seems like the same overall activity that we see here. We can almost see the same 22 hertz or so slow oscillations, but we also have faster ones. And this could be likely related to the individual spike times that we're seeing. And so you are getting here in the power spectra, you're getting all these strong power from the fast frequencies of the individual spikes, I believe. And so it's showing a much stronger activity here in the higher frequencies, in the gamma range, high gamma. But again, this I believe is an artifact of having very simplified cell models. So if you had like morphologically detailed ones, you might be able to see a more realistic effect and the slower oscillations having a stronger power. Well, thanks for the question. This was useful to illustrate how to add new plots. I'm just going to remove these two guys. And now I think it's also a good time to show that you can plot these plots interactively. So after the simulation has run, if you wanted to plot the LFP, you could just say sim analysis plot LFP, include, for example, just the spectrogram. Second. It was probably mistyped something. Equal. Okay. Should work. So yeah, so you can access all the plotting functions directly through the sim analysis module and use these functions interactively here. So you get the same result. And you can also inspect both here or in the documentation, all the different analysis functions that you have. Things like, even for example, for spikes, you have some spike statistics that you can plot. So if you wanted to do that, you could come here and type plot spike. And you will get statistics of the different populations. In this case, we just have two populations here, the excitatory and inhibitory cell type. This is the average firing rate, or the statistics of the rate with the median, and here's the mean, and the interquartile range, typical box plot, and this is the interspike interval coefficient of variation. So there's a bunch of analysis functions that are built in and that you can use with any of the models, the NetPyNE models. Okay, so if there are no other questions, I'm gonna go ahead and modify some of these parameters to show different oscillations. So the first example we have here is setting this I to E connection probability to 0.0. So this one here, so the connection that goes back from inhibitory to excitatory, we can set it to 0. We can run the network. And we will see a significant change in the results. So we see that now the synchrony has essentially disappeared. You have these red lines all across the raster plot, indicating that the cells are not really firing together in little groups. And so you again do not see these clear oscillations in the network, in the spike histogram. And it's also disappeared from the firing rate spectrogram. So this strong peak that you had at 22 hertz is gone. And you have now these high frequencies, which are actually closer to what you saw in the LFP. So that means that you require having these inhibitory connections to ensure that you get oscillations in it. So we're just gonna put that value back here. And we're gonna modify something else. So we're gonna change the delay, the connection delay of these inhibitory connections from 5 milliseconds to 20 milliseconds. I'm gonna run the network. Okay, so we're essentially seeing that the network oscillation frequency has now slowed down. So we see, if we count these groups of red lines, we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hertz approximately. And we also see this in the spike histogram and very clearly represented in the spectrogram. So it's now gone down to around 15, 16 hertz, just by changing some of the dynamics in the network and very quickly visualizing it here in the Google Colab Jupyter Notebook. So essentially what's going on here is that by changing this delay, the response, the inhibitory input to the excitatory cells takes a bit longer. So you're slowing down the whole process. And you see these gaps are slightly longer now, leading to the slower oscillations. So we can put back the original value back to 5 milliseconds. And now let's try another change. So we can also do the same with the decay time constant here of the synaptic mechanism, the inhibitory synaptic mechanism. We can change it from 5 to 20 and run the simulation. And so what we see is that this has decreased significantly the oscillation frequency, although also the sort of overall strength of the network oscillations. So now it's really slow. Now we're getting about, yeah. So we're getting about 10 hertz or so. We can see that here as well in the spike histogram, and not so clear in the spike in the spectrogram because the power of the oscillations is very low now. So I believe there was another parameter we could change to increase the overall strength. I'm not sure if increase this probability a bit higher. Yeah, so if you increase now the probability of connection up to 0.9, that makes the inhibitory connections a bit stronger. So you can see this slower oscillation. So you have a very strong synchrony, less activity overall, and you get this oscillation, which is now around 9 or 10 hertz. There's also some other peaks here in the spectrogram, but we have basically reduced from the initial 22 hertz, then to 15 hertz, and now to 10 hertz oscillations. You can see that playing around in the network parameters, you can make all these changes. And are there any questions about this? Which method do you use for time frequency analysis? It seems to be SDFT. Yes, so the method we are using, we can actually check here. It's it's the Morlet wavelet method. That's the default. Before we were using the normal FFT, but we changed to Morlet wavelet because it had more resolution in the frequency domain. And you can, I believe you can still change to the older FFT method. If you change the transform method here. And yeah, you can change many of the parameters here. As you see, there's a bunch of things you can modify to get the whatever spectrogram you want to plot. Okay, any other questions? If not, I just wanted to take the time here at the end to show very briefly that you can do the same thing also within the NetPyNE GUI. So as Joe mentioned before, if we go to the GUI has a built-in Jupyter notebook. And so the same thing we have done in the Colab, we could have done directly in the Jupyter notebook. And the nice feature there is that we can then synchronize with the GUI itself and visualize the same results within the GUI. So I'm just going to try to show that. So if we open the Jupyter notebook here at the bottom, we can go to our Google Colab and just copy over the code. Yeah, so the steps are shown here also in the slides. Then we go to the Colab, and if I copy this code and just put the original values, 0.7 here, I just copy this, and I think if I pay this straight away, it should work. So it's running the network and showing the same plots that we got in the Google Colab. There's this frequency here. And the nice thing that we can do now is that we can tell the GUI to sort of load these results into the GUI. And to do that, we just need to copy these two commands. I'll put them in the chat. Okay. So this is telling the GUI to load the parameters that we're specifying here at the root level, netparams and simconfig. Okay, so after running that command, we now see the same model that we defined programmatically. We can see it straight away here in the GUI. If we click on pyramidal cell, and we look at the sections, we see the soma with the geometry, 18.8 and so on. We can see the populations, excitatory and inhibitory, 20 cells each. And let me just illustrate what I mentioned before, which this showing that this is fully synchronized. So if I do netparams, popparams, and I check the E population, I will see the cell type pyramidal, number cells 20. If I change this to 15, oh, this is, sorry, this is the inhibitory. Change the excitatory one to 15. And I now check again here in the Jupyter console. This has changed here, number of cells 15. And I can also just set it back to whatever number, 25 here on the Jupyter notebook. Oh, sorry, I forgot to specify num cells. Okay. I might have messed it up because I set the wrong parameter. Let me just check. Yeah. So let me just reload the model again. Okay. Okay, so now that's fine. Previously I overwrote the whole structure, but now it's fixed. I just reloaded the code. And I click here, this is 20, and I can change it to 25. Oops. Let's reload again. Okay, so gonna run this code. Okay, I'm gonna make those parameters part of the GUI. So now you can see. Okay, let me just get a fresh one, because I think I messed it up. Okay, so I just go to my Jupyter collab, Jupyter Notebook collab. I paste here, points over here. So I run this cell. And then I run this code. Okay, so now I have again the populations. The cell type here, the populations are here, and this is 20 cells. So I now want to change smaller. I want to change the number of cells via the Jupyter Notebook. So the E population, the number of cells is 20, and I want to change it to 25. So that changes here, both in the GUI and in the console. It's going to change back to 20. Okay. And similarly, of course, you can create the network itself. So these are the 20 very simple cells, just a cylinder, and you can run the network. And you can see some of the same plots that we saw before, but via the GUI. So we see the voltage traces, we see the raster plot, the spike histogram, and I think those are all. Okay, so that's just to illustrate that we can do basically the same things from programmatically via coding, via Jupyter Notebook Colab, for example, or via the GUI, and that they can interact with each other. Okay, so I think that concludes. So just to finish, I wanted to remind you of the different resources you have. So if you go to the website, that's netpyne.org, from there you have links to most of the stuff. These slides with several of these links as well are available here, bit.ly. The YouTube channel, please take a second to check it out. We have many different videos from both workshops and tutorials. We will also post the videos from this tutorial. But if you go to playlists, for example, the NetPyNE course 2021, that's almost 40 hours of in-depth courses on NetPyNE, much more advanced than what we saw today. Today was a very simple introduction, but we have courses on starting from some introduction in Neuron and some Neuron basics and RxD. We have exercises for each of the courses. And then we go into NetPyNE using the GUI, different tutorials for the GUI programmatically, some details, some lectures on building these very complex multi-scale models, parameter optimization as well, combining NetPyNE and RxD, and a bunch of speakers also who have used NetPyNE to build different models. And you have the recorded talks here of all the 10 different speakers that spoke at the course. Okay, and I think that's all for now. So if you have any questions, please do feel free to contact us. This is also open source. So we have a GitHub repo where you can post any issues. And we're always happy to help as well to build your models and add any features that you require. So, thank you so much, everyone.
I just want to say also, thank you to my thank yous to the participants and the speakers. I also want to point out that on the chat and on the Discord, in case the chat disappears before you get around to it, there is a Qualtrics survey form. You can. We would love to know how you thought that this tutorial went and what you think we could do better in the future. It's anonymous, as far as I know. I have no way of tracking anything down. So we'd love to hear any sort of feedback that you want. And obviously, I know for myself, and I assume for everybody else that spoke today, if you want to talk to us directly, we're certainly happy to address your questions and concerns directly as well. So, many thanks. Please fill out the survey.